Hello there and welcome to Life Beyond Seen, where curiosity settles in like a soft blanket and science takes its time wandering through the strange corners of the world. Tonight we're drifting somewhere most people never imagine when they picture the ocean. Not the bright shallows, not the gentle tides, not the calm blue surfaces you might see from a beach or a boat. Instead, we're going to step quietly into the darkest water on Earth. A place where sunlight never reaches, where pressure rises to levels that would crush a submarine, and where the floor of the planet breaks open and releases water so hot it could melt lead. It may sound like the last place any living thing would ever want to be, but it's here, in this boiling darkness, that some of the most remarkable forms of life have found a way to thrive. These are the worlds around black smokers, the deep-sea vents that breathe mineral-rich plumes into the midnight ocean, shaping ecosystems unlike anything found at the surface. Before we make our way down through the layers of water and into that hidden landscape, I'd love to know something simple but grounding. Where are you listening from tonight? And what time is it in your little corner of the world? It's always interesting to imagine people scattered across different rooms, beds, sofas, cities and time zones, all arriving at this quiet moment together. The deep sea feels distant, but here you are, and here I am, sharing the same stretch of words, even if the clocks around us aren't quite aligned. If you find this slow drift into science soothing, or if you enjoy wandering through strange environments without needing to adjust your pillows or stand up from wherever you're settling in, I'd be grateful if you gave the video a like or even subscribed. It helps this calm little channel find more people who might need a peaceful place to rest their thoughts for a while. So let's start at the surface, far above those vents where the ocean seems ordinary. Imagine floating near the top of the sea on a quiet night, the kind where the air feels cool and the waves move with a steady rhythm. There's nothing unusual here, just the familiar world of currents and starlight reflected on the water. But beneath that surface is a vertical journey so long it almost feels unreal. A descent into darker and colder water, layer after layer, until the familiar world fades and something completely new begins. Most people never think about how deep the ocean truly is. Even ships that cross it for weeks only skim the top. Light stops travelling after a few hundred metres, and everything below that exists in permanent darkness. As we imagine ourselves descending, the colours fade. Blues become darker, then disappear. Sounds change. Water pressure builds with every metre, squeezing tighter than anything you've ever felt. Fish becomes scarcer. The temperature drops. It starts to feel like entering another planet, one that happens to lie just beneath our feet. And if we kept going down even further, kilometres into the deep, we'd eventually reach a point where life seems almost too sparse to continue. Most of the creatures here move slowly, conserving every bit of energy they can because food drifts down from the surface in little more than crumbs. It's a world filled with patience, a world where motion is rare and light is non-existent. Yet this isn't where we're stopping. We're heading for a place that contradicts almost every expectation about the deep sea. Imagine moving over a plain of soft sediment, the ocean floor stretching out like a vast desert. Then you notice something strange in the darkness. First a faint shimmer, then a shifting cloud, and finally a jagged structure rising out of the ground like a tower built in secret. And there, pouring from its top, is water so hot and dense with minerals that it looks almost like smoke. These are black smokers, hydrothermal vents created when seawater seeps into cracks in the Earth's crust, heats up to extraordinary temperatures, mixes with minerals, and shoots back out in dark, swirling plumes that billow upward. The scene is unlike anything else in nature. These vents can stand as tall as buildings, with smoke pouring from their openings in a constant eruption. The water around them shifts and sways with the heat, forming strange currents. Minerals precipitate the moment they hit the cold seawater, causing the chimneys to grow, twist and crumble over time. It feels alive even before you notice the actual organisms. And then you notice the living things, not timid or sparse, not fragile or cautious, but thriving in places where life should struggle to exist. Clusters of tube worms growing like bright pale forests, mussels clinging to the rocks in enormous groups, ghostly crabs exploring the chimneys, microbes floating in the heated water, using chemicals instead of sunlight to power their existence. These organisms don't just tolerate the vents, they depend on them. The vents create the energy they need, and they form entire ecosystems around that single source. It's a strange thought. We grow up thinking that life needs sunlight, plants rely on it, animals depend on the food chains built from it, and every outdoor scene we picture is shaped by it. But down here, sunlight has no meaning. The organisms don't use it, don't miss it, don't even know it exists. Instead, life is fueled by chemical energy released from deep inside the earth. It's a world built on heat and minerals rather than light and warmth. And as we look at this environment, it's natural to feel a sense of wonder about how life manages to survive in a place that seems so hostile. The water near the vents can reach temperatures far higher than boiling, yet just a short distance away the water is near freezing. The pressure would crush human lungs and bones in seconds. The minerals released can be toxic. The darkness is absolute. Yet here, surrounded by conditions that appear unforgiving, life has carved out a space for itself that's not just functional, but thriving. While the vents roar and bubble, the organisms around them carry on with their lives. The tube worms extend their plumes to absorb chemicals from the water. Bacteria living inside them convert those chemicals into food. Giant clams open and close slowly, filtering the water. Crabs scuttle across the chimneys, picking at whatever they can find. Shrimp cluster in dense swarms, navigating the shifting temperatures with uncanny accuracy. Nothing about it feels accidental. It's a complete community, one shaped not by gentle sunlight or calm waves, but by the raw power of Earth's interior. Before we get deeper into how these ecosystems function, or how such organisms evolved, it's worth staying a moment longer in this initial scene. There's something grounding about imagining a place so separate from our daily world yet entirely real. No sound of traffic, no glow from streetlights, just the slow rumbling of the earth, the hiss of superheated water, and the gentle movements of creatures shaped by an environment that seems almost impossible. The contrast itself is part of the fascination. At the surface we live with routines, day and night, weather patterns, seasons. We know when the sun will rise. We know how warm or cold the world might be, but down here everything is different. There is no sunrise, there are no clouds. The temperature can swing drastically from 1 meter to the next. Pressure changes aren't something you feel on your skin. They're forces that shape what life can exist at all. In a way, this environment feels like a reset button on our assumptions about what life needs. And once you spend a little time thinking about this place, you start to understand why scientists became so fascinated with it when hydrothermal vents were discovered in the late 1970s. Before then, most people assumed the deep sea was quiet, sparse, and largely empty. The idea that vibrant ecosystems could exist in total darkness wasn't widely considered. When researchers first saw tube worms taller than a person, and vents spewing black fluid that looked like a chimney releasing smoke, it changed our understanding of biology itself. Even now, decades later, exploring these places continues to reshape our thinking. They raise questions not only about how life works, but also about where life might have begun. Some scientists believe early Earth might have hosted environments much like these. If that's true, then the first living things may not have emerged in sunlight but in heated, mineral-rich water near vents very similar to these ones. It's a compelling idea, and one we'll eventually spend more time exploring as we continue through this journey. For now, though, it's enough to let the image settle. A dark world lit only by shimmering particles and the faint glow of bioluminescent organisms. water hotter than anything you would ever want to touch, minerals forming chimneys that rise like towers, and life, steady and certain, moving in ways that feel both alien and familiar. It's a reminder that the Earth holds secrets far below our daily experiences, secrets that exist even when we're not thinking about them, secrets that keep revealing new details every time we look a little closer. We've only just begun to explore this strange landscape. There's so much more happening in these depths than first meets the eye. The chimneys themselves have stories. The chemicals fueling life have pathways that intertwine. The creatures have adaptations that seem almost unbelievable. And the geology shaping the vents is part of a larger system that affects the entire planet. We'll keep moving through all of that, staying grounded in the details rather than rushing. After all, there's no hurry here. The ocean has been doing this for millions of years. The vents have been building and collapsing, feeding communities and shaping ecosystems long before we ever knew they existed. And now that we're here, imagining this deep environment together, we can let the story unfold, piece by piece, without pushing toward an ending. When we shift our attention next, we'll start looking more closely at the dark plains that surround these vents, and the way this seemingly empty landscape sets the stage for everything that follows. But for the moment, it's enough to stay near this first glimpse of the black smokers and appreciate how unusual, resilient, and quietly remarkable life can be when the world above doesn't shine a single beam of light into the water below. When we move away from the vents for a moment and turn our attention to the world that surrounds them, it becomes clear just how unusual these places really are. The deep ocean isn't just dark, it's a level of darkness that defies comparison. It isn't like a room with the lights off or a cave you might walk through on a tour. Those spaces always have an exit sign glowing somewhere, or a hint of brightness that your eyes can adjust to. Down here, there's nothing. Your eyes don't adapt. Your pupils don't widen enough. The darkness is absolute. A steady presence that settles in all directions without a single point giving way to even the faintest glow. The events themselves aren't light sources either. They release shimmering particles of minerals that scatter the water, and sometimes creatures nearby flicker with bioluminescence. But that's not the same as illumination. It's more like tiny reminders that things exist in a world where vision is almost useless. This darkness shapes everything. It influences how creatures move, how they find food, how they sense their environment, and even how their bodies are built. Many of the animals here don't have eyes at all. Others have eyes that work differently from anything on land because they aren't looking for sunlight. They're looking for faint glimmers from other organisms or the reflections of minerals swirling in the heated water. It's a strange thought that vision, something we rely on constantly, becomes optional or even irrelevant at these depths. But that's how life works when light is removed from the equation entirely. The animals adapt, not by searching for a new source of brightness, but by reshaping their world around the absence of it. The pressure down here adds another layer of complexity. We sometimes use the phrase crushing pressure casually, but it's worth pausing to consider what that actually means. Every 10 meters of depth adds another layer of weight equal to the pressure at the surface. Go down 1,000 meters and you have the equivalent of almost 100 atmospheres pressing on your skin. Drop to 2,000 meters and the pressure becomes something unimaginable to the human body. At the depths where black smokers are found, the weight of the water above is so immense that our lungs would collapse instantly. Our bones would not hold. Any unprotected machinery would either implode or fail in ways that would make repairs impossible. Yet the creatures here don't just tolerate this pressure, they're built for it. Their cells contain adaptations that allow membranes to stay flexible. Their proteins function only under immense weight. Their bodies lack air-filled spaces that would collapse under the strain. It's not that they're strong enough to resist the pressure, it's that the pressure is simply the environment they evolved in, as normal to them as the atmosphere is to us. If anything, bringing one of these animals to the surface is far more dangerous to them than staying where they are. Up here, their proteins unfold, their membranes lose stability, and their entire biology breaks apart because it's no longer in the conditions that hold everything together. It's not just the animals that feel this pressure. The vents themselves, the chimneys and openings where the heated water escapes, are shaped by it. The hot fluid that bursts out of the ground is under extraordinary internal force, and when it meets the cold seawater, the minerals inside it solidify rapidly. This creates layers of sulfides and metals that form the structures towering above the seafloor. These chimneys can grow quickly, sometimes centimetres per day in the right conditions, but they can also collapse just as suddenly. The entire landscape is in constant flux, driven by a balance between heat, chemistry, pressure, and water flow. One day, a vent might be releasing plumes of dark fluid, feeding an entire community around it, and the next it might seal shut or break apart because the stresses around it have shifted. As we picture this dark, high-pressure environment, it's easy to imagine it as hostile or empty, but in reality, it's more like a world waiting for something unusual to ignite its potential. Everywhere around the vents, the deep sea is filled with fine particles drifting down from the surface. Bits of dead organisms, fragments of broken shells, small clusters of organic material from the upper layers of the ocean. All of it rains slowly through the water column until it reaches the bottom. The animals living far from the vents rely on this slow supply of food. They move slowly and eat slowly because they must. There simply isn't enough energy available for constant activity. Every motion counts, every bite matters, and every scrap of falling organic matter can determine whether a creature thrives or barely survives. This creates a world built on waiting. Waiting for food, waiting for movement, waiting for anything that breaks the stillness. If we imagine standing, if standing were possible, on one of these plains of soft sediment, the silence would be overwhelming. Everything moves at a pace we're not used to. A sea cucumber might drift across the ground at a rate so slow you'd have to watch for minutes before noticing progress. A deep-sea fish might conserve its energy by hovering in place for hours. It's a place that doesn't reward speed or surplus motion. Instead, life spreads itself thinly across the landscape, adapting to an environment where resources rarely arrive with any urgency. And then, in the middle of that quiet expanse, a hydrothermal vent can change everything. Suddenly the surroundings are no longer just dark and cold. They become rich with energy. Not energy from the sun, but energy from the earth itself. Hydrogen sulfide pours out from the cracks, and this gas, poisonous to most surface creatures, becomes the foundation for growth. Bacteria rush to use it. They attach to surfaces, gather into swarms, form mats, and begin the process of converting chemical energy into usable organic compounds. Everything else in the ecosystem builds on that initial step. If the deep sea beyond the vents feels like a slow desert, then the area around the vents becomes a bustling oasis, not in terms of speed or noise, but in terms of density and activity. This dramatic contrast between scarcity and abundance shapes how organisms evolve here. Life around the vents must be ready to take advantage of sudden changes in energy availability. A vent might start producing more minerals, it might shift its flow, it might release more heat, it might cool down, it might vanish entirely. These changes aren't predictable on short timescales, so the animals that live here have adapted to shift their behaviours and physiologies when needed. Tube worms grow rapidly when conditions are right. Mussels form dense clusters where nutrients flow strongly. Shrimp gather near areas that warm slightly. Crabs roam across the chimneys, picking apart whatever they can find. This flexibility allows them not just to survive, but to flourish as long as the vent remains active. But nothing in these depths lasts forever. The vents eventually collapse or clog or shift. When that happens, entire communities must relocate or decline. Some organisms drift in search of new vents, enabled by larvae that travel through the water column until they detect the right chemical signals. Others die out if the change happens too suddenly. Some species rely on vents so completely that they cannot survive anywhere else. It creates a pattern of growth, collapse, regrowth, and migration that defines the ecology of these regions, forming cycles far different from the predictable rhythms of surface ecosystems. It's tempting to imagine the deep sea as static, but everything here is shaped by motion. Slow motion, powerful motion, and sometimes catastrophic motion. The ocean floor isn't a flat surface. It shifts, opens, closes, and resettles constantly. We live on a planet with plates that move, grind, and pull apart. The mid-ocean ridges where black smokers are found are places where the crust is actively forming. New rock emerges slowly from below. Old rock pushes aside. The vents are symptoms of this activity, signs that the planet is alive in a geological sense, and every change beneath the surface eventually affects the life above it, even if the connection isn't obvious at first glance. What's striking about this world is how well life fits into these cycles. The organisms aren't fragile anomalies. They're not exceptions struggling to survive. They are perfectly matched to their environment, even when it changes dramatically. They show us that life doesn't require stability to succeed. It needs opportunity and adaptability. It needs something to build on, and once that foundation exists, it expands outward in directions we might not expect. When we think about life on Earth, it's easy to assume that the surface conditions are universal, that sunlight and oxygen and moderate temperatures are the baseline from which everything else deviates. But the truth is more complex. Life began on a planet that was far less gentle than the one we live on now. There were more impacts, more volcanic activity, more fluctuations in temperature, and more environments that would feel completely uninhabitable to us today. Yet life persisted, adapted, and diversified. The deep ocean vents remind us of that history. They show us environments where chemical energy drives ecosystems, where biology continues even when the most familiar ingredients are missing. When we look at the animals here, we aren't seeing outliers. We're seeing examples of how flexible and inventive life can be when faced with enormous challenges. The pressure, the darkness, the temperature gradients, the uncertainty of resources, all of it becomes part of the structure of life rather than an obstacle that prevents it. If anything, these organisms make it clear that life doesn't flourish because conditions are perfect. It flourishes because it finds ways to make use of whatever conditions exist. As we stay in this dark, pressurized world a little longer, it becomes easier to understand why scientists consider these vents such important places for studying biology. They force us to rethink assumptions about what life needs. They show us that energy can come from heat and chemistry, not just from the sun. They demonstrate how ecosystems can assemble themselves in environments that appear hostile at first glance. And they encourage us to look beyond the familiar when imagining where life might exist elsewhere in the universe. There's more to explore here, more details to uncover about how these organisms function, how they interact, how their bodies handle the extremes around them, and how the vents themselves behave over time. But we'll move toward that gradually, without rushing away from this view of the deep sea world that surrounds the vents. It's a landscape shaped by darkness, pressure, and possibility. A place where life thrives not by overcoming the environment but by becoming part of it. When we look more closely at the structures rising from the seafloor around these vents, it becomes clear that they're not just simple piles of rock or random formations created by chance. They're chimneys built by the ocean itself, shaped by heat, minerals, pressure, and time, forming slowly at first and then sometimes growing with surprising speed. These chimneys are called black smokers because the fluid that spills out of them looks like dark smoke pouring from a furnace. But it isn't smoke, and the chimneys aren't solid stone in the way we normally think of stone. They're towers formed from minerals that harden as soon as they touch the cold seawater, layer after layer stacking themselves into tall structures that can reach several stories high. It's strange to imagine that something so stable looking is actually the result of constant chemical reactions. Deep beneath the ocean floor, water seeps into cracks in the crust through tiny openings. As it sinks, the water encounters rock heated by magma, and the temperature rises far beyond anything we usually associate with the ocean. The water becomes superheated, reaching temperatures well over 350 degrees Celsius. But because it's trapped under extreme pressure, it doesn't boil the way it would at the surface. Instead, it becomes a pressurized, mineral-rich fluid capable of dissolving metals and sulfides from the surrounding rock. Once the water reaches its maximum heat and mineral load, it rises back upward through cracks and channels until it finds an opening in the seafloor. When it escapes into the cold water surrounding it, everything changes at once. The sudden drop in temperature forces the minerals to solidify rapidly, forming black particles that billow upward in dense plumes. Over time, these particles coat the edges of the opening, building up a chimney that continues to grow as long as the vent remains active. The result is a structure that feels both temporary and ancient. It might stand tall for years, but it also has the potential to collapse without warning if the internal flow shifts, or if the minerals weaken under the constant stress of hot water passing through them. The appearance of these chimneys is striking. They can be narrow and straight like pillars, or wide and branching like frozen fountains. Some lean slightly, shaped by currents that push against them day after day. Others stand tall and straight, rising out of the seafloor like towers built with a deliberate hand. The surfaces are rough and uneven, textured with countless layers of minerals that give each chimney its own shape and character. Some of these minerals sparkle faintly in the dim light of a submersible's cameras, but to the creatures living here, these chimneys are simply the backdrop to their world, the structures that host the heat and nutrients they depend on. The water spilling out of the chimneys is one of the most remarkable features of the environment. It doesn't mix evenly with the surrounding seawater. Instead, it forms cloudy plumes that twist and rise before gradually dispersing. These plumes carry the chemicals needed for chemosynthesis, the process by which bacteria convert chemical energy into food. To us, the plumes might look ominous or strange, but to the organisms that live here, they're a source of life. The boundaries where the hot fluid meets the cold seawater create temperature gradients, and many creatures position themselves carefully along these gradients, finding the precise spot where conditions are right for their survival. The chemistry of the vent fluid is another key feature. It contains hydrogen sulfide, iron, manganese, copper, zinc, and a range of other dissolved elements that would be toxic to most organisms on the surface. The water is acidic, often carrying a pH far lower than anything we'd consider safe for fish or marine plants. It's an environment shaped entirely by geology rather than sunlight, and the organisms that live here have evolved to take advantage of this unusual chemistry rather than avoid it. When we imagine a chimney erupting with superheated water, it can be easy to think of it as a chaotic process. But there's a surprising amount of structure and consistency to how these vents behave. The fluid flows upward at steady rates, maintaining temperatures and chemical compositions that can remain stable for years. The chimneys grow in predictable ways, always building around the openings where the vent fluid escapes. When a vent shifts or changes, the chimneys react accordingly. Some begin to crumble, some grow faster. Some stop forming entirely, leaving behind hollow, brittle shells that may eventually collapse and fall to the seafloor. These structures aren't just random geological formations, they're essential parts of the deep-sea ecosystem. They provide surfaces for bacteria to grow on. They create sheltered pockets where small organisms can hide from predators or currents. They establish patterns of water flow that influence how nutrients move through the environment. Without the chimneys, the vents wouldn't function in the same way. The entire system depends on the interaction between hot fluid, cold seawater, minerals, pressure, and time. The temperature differences around the chimneys can be dramatic. Just a few centimetres from the opening, the water can shift from near boiling to near freezing. This creates microhabitats where different organisms cluster depending on their tolerance for heat. Some microbes thrive in the hottest water, clinging to the edges of the vent opening. Others prefer slightly cooler temperatures and grow in dense mats on the outer surfaces of the chimneys. Larger animals like tube worms and mussels often live at a comfortable distance from the vents, close enough to access the chemicals they need, but far enough that the heat doesn't overwhelm them. This delicate balance means that the chimneys act as organisers of the ecosystem, shaping not just the landscape but the distribution of life around them. Each surface, crevice, and gradient becomes an opportunity for different species to establish themselves. Some creatures attach themselves directly to the chimneys, others burrow into nearby sediment. Some float or swim in the plumes, drifting through the heated water as they filter out nutrients or hunt for prey. Everything is arranged around the structure and behaviour of the chimneys, creating an environment that feels both organised and unpredictable at the same time. The growth of a chimney can be surprisingly fast under the right conditions. When the vent fluid is rich in minerals and the flow is steady, the chimney can develop new layers rapidly. In some cases, chimneys have been observed growing more than 10 centimetres in a single day. Over weeks and months, this can transform the landscape dramatically. A small opening in the seafloor can become a towering structure. A narrow chimney can thicken and branch. Old sections can crumble while new ones emerge. The entire area becomes a living construction site, not because any organism is building it intentionally, but because the chemistry and physics of the environment are constantly interacting. The fragility of these chimneys is part of what makes them fascinating. They look solid, but their composition is brittle. The minerals forming them are often sulfides that crack easily under stress or temperature changes. A sudden shift in the vent's flow, a slight change in temperature, or an alteration in the surrounding currents can cause pieces of the chimney to break off. Sometimes these collapses create opportunities for new vent openings to form. Other times they disrupt established communities, forcing organisms to relocate or adapt. The chimneys aren't permanent features. They're temporary expressions of a process that continues beneath the surface, shaped by forces that never stop moving. Despite their temporary nature, the chimneys leave behind traces long after they stop functioning. When a vent becomes inactive, the mineral structure remains for a time before it erodes or collapses. These remnants provide clues about past activity. Scientists studying them can determine how long the vent was active, what types of minerals were deposited, and what conditions existed in the surrounding area. It's like reading a geological diary written by the ocean itself, one that tells stories about heat, chemistry, and change. The shapes of the chimneys vary widely. Some are slender and delicate, with narrow openings that release plumes straight upward. Others are broad and sturdy, with multiple vents scattered across their surfaces. Some develop branching forms as minerals build up unevenly. Others resemble twisted tubes or stacks of plates. The diversity of shapes reflects the diversity of conditions at each vent. Different mineral compositions lead to different structures. Different flow rates create different textures. Different temperatures influence how quickly the chimneys grow or collapse. Every chimney becomes a physical record of the vent's behaviour, shaped by the specific circumstances of that point on the ocean floor. One of the most remarkable things about these chimneys is how they create order in an otherwise uniform environment. The deep sea floor in many regions is flat and covered in sediment. There are few landmarks or variations, but when a vent becomes active, everything changes. The chimneys rise from the ground, creating height and texture. They channel water flow. They divide communities into zones. They attract organisms from far away, often via larvae drifting in the water column. They turn a quiet plain into a bustling centre of life. The landscape becomes layered and complex, not by design, but by the natural interactions between heat, pressure, and minerals. The colours of the chimneys may surprise anyone who imagines the deep sea as entirely grey or black. While they often appear dark in videos, their mineral content can create subtle variations in colour. Iron can give parts of the surface a reddish tint. Copper can create blue or green hues. Zinc and sulphur can introduce pale or yellowish tones. These colours aren't vivid in the darkness, but under artificial light they reveal themselves in small patches and streaks, hinting at the diverse chemistry within the structures. When we consider the heat coming from these chimneys, it's worth remembering that the surrounding water is cold enough to freeze your skin in seconds. The deep sea maintains temperatures just above freezing. This contrast creates a tug of war between two extremes. The chimneys release water that's hot enough to melt many metals, but only centimetres away the water is cold enough to slow biological processes dramatically. Organisms that live here navigate this terrain with precision, finding the spots where temperature and chemistry align with their needs. The more we explore these chimneys, the clearer it becomes that they are dynamic systems rather than static formations. They grow, shift, and disappear. They respond to geological forces, chemical changes, and biological activity. They support entire communities and shape the way those communities interact. They're constantly being rebuilt by the interplay of hot fluid and cold seawater. And they remind us that the deep sea, despite its vast stillness, is full of change. There's more to explore around these chimneys, including the organisms that gather near them and the chemical processes that sustain the entire ecosystem. But the chimneys themselves serve as a foundation. They create the environment where life can flourish, and they continue to influence everything that happens around them. As we move forward, we'll look more closely at the creatures that depend on these structures and how they navigate the unusual conditions created by the boiling water rising through the ocean floor. When we turn our attention toward the living creatures that gather around the black smokers, it becomes clear just how different this part of the ocean is from anything we're used to. Life here doesn't resemble the colourful reefs with their fast-moving fish and swaying corals. It doesn't mirror the surface waters where sunlight filters through and plants drift in gentle currents. Instead, this is a world where animals bloom in the heat, rising from the vents, clustering together in ways that seem almost impossible given the cold, dark, pressurized environment that surrounds them. These organisms depend entirely on the chimneys for survival, and each species has its own way of dealing with the heat, the chemicals, and the constant changes happening around the vents. One of the first creatures people notice when they see footage of hydrothermal vents is the giant tube worm. These worms don't look like anything familiar from beaches or shallow water. They grow in tall, dense clusters, each worm encased in a long white tube that can reach lengths of more than 2 meters. Near the top of each tube is a bright red plume that resembles a soft brush or a carefully shaped cluster of elongated petals, though it's not plant-like at all. The red colour comes from hemoglobin, the same molecule in human blood that carries oxygen, but here it's adapted to carry not just oxygen, but also hydrogen sulfide, a chemical that most surface animals can't tolerate. The plume isn't the mouth of the worm, it's more like a respiratory organ that draws in the chemicals and gases needed by the bacteria living inside the worm. This relationship between the worm and the bacteria is essential. Tube worms have no mouths, no stomachs, and no digestive tracts. They don't eat in the way we understand eating. Instead, the bacteria inside their bodies perform chemosynthesis, turning hydrogen sulfide from the vent fluid into nutrients that keep the worm alive. The worm provides a safe environment for the bacteria, and the bacteria provide food in return. It's a relationship so complete that neither organism can function properly without the other. The worms cannot survive without their internal bacteria, and the bacteria depend entirely on the worm to deliver the chemicals they need. Clusters of tube worms often mark the first sign of life when a new vent becomes active. Larvae drift through the deep sea and settle when they detect the right chemical signals. Once the first few worms establish themselves, their presence helps shape the environment by creating sheltered pockets and catching drifting material. Over time, the clusters grow larger, forming dense patches that stand out clearly against the dark background of the seafloor. These gatherings are not delicate or sparse, they're thick layered communities with worms of different ages and sizes growing close together. Nearby, mussels form their own gatherings. These mussels are related to the ones people might see in tide pools or attached to rocks near the shore. but they've evolved to live in conditions that would be lethal to their shallow water relatives. They attach themselves to rocks or the mineral surfaces of the chimneys, forming large groups that sometimes cover entire sections of the vent area. Unlike tube worms, mussels do have mouths and digestive systems, but they rely heavily on bacteria living inside their gills to convert chemicals into food. This dual approach allows them to take advantage of both particles drifting through the water and the chemical energy from the vent. The shells of these mussels are often darker than those of surface-dwelling species, a reflection of the minerals that accumulate on them. The mussels open and close slowly, drawing water through their bodies and filtering it for nutrients. They stay close enough to the vent to access hydrogen, sulfide and other chemicals, but far enough away that the extreme heat doesn't damage their tissues. Over time, small differences in water flow and chemistry lead to variations in how densely these mussels cluster and how large individual mussels can grow. Some thrive in slightly warmer areas with more chemicals available, while others prefer the cooler outskirts of the vent field. Crabs play another important role in these vent communities. These aren't the brightly coloured crabs found in coral reefs or tide pools. Most deep-sea vent crabs are pale, often white or off-white, because there's no need for pigmentation in an environment without light. Their eyes are reduced or absent, and their legs are built for navigating the uneven surfaces around the chimneys. These crabs are opportunistic feeders. They pick up bacteria, scrape particles from surfaces, and steal bits of food from other organisms. They move slowly but consistently, exploring cracks and crevices for anything edible. Some species congregate in surprisingly large numbers around vent openings, drawn by the warmth and the abundance of microbial life. Their movements can appear chaotic when viewed up close, but they follow chemical cues that guide them toward areas where food is most likely to be found. The density of crabs varies depending on the age and activity of the vent. Newly active vents might attract fewer crabs at first, while mature vents can support substantial populations. Shrimp are another striking presence near the vents. Certain species hover in clusters so thick that they form moving blankets over the chimneys. These shrimp have specialised adaptations that allow them to sense the heat from the vent and position themselves within a narrow range of temperatures. They rely on bacteria as part of their food source, sometimes scraping microbial growth from surfaces or filtering the water for particles. Some species have reflective surfaces on their bodies that help shield them from the intense infrared radiation emitted by the vent openings. Their movements can look frantic, especially when currents shift and the temperature changes suddenly. But each shrimp is responding to precise signals in the water, moving toward heat when conditions are safe and away from it when the temperature rises too high. These shifts can happen in moments, and the shrimp adjust without hesitation, their bodies finely tuned to the environment. There are also fish that live near the vents, though they're not as visually dramatic as the shrimps or tube worms. Many are small and pale, with reduced pigmentation and slow movements. They hide among the rocks and chimneys, feeding on small animals or drifting particles. Their presence is a reminder that even animals with more familiar forms can adapt to life in these unusual conditions. They don't rely on the vent chemicals directly, but they benefit from the abundance of organisms that do. One of the most fascinating aspects of these vent communities is how quickly they can develop when a new vent becomes active. Everything begins with microbes. These bacteria and archaea are the first to take advantage of the chemical energy. They grow on rocks, in the water, and even within the vent openings themselves. As microbial colonies expand, they create a food source for other organisms. Larvae drifting through the water detect the chemical signatures and settle in the area. Tube worms anchor themselves, mussels attach to available surfaces, shrimp gather where the chemistry is suitable. Fish move in as the community grows. Within months, a previously barren stretch of seafloor can become dense with life. This rapid growth is balanced by the instability of the environment. If the vent shifts or the chemistry changes, some of the organisms must relocate. Tube worms can grow quickly, but they can't move once they've settled. If the conditions become unsuitable, they may die off, leaving behind empty tubes that create new structures for other creatures to use. Mussels can survive for a time without the same level of chemical input, but they eventually decline if the vent becomes inactive. Shrimp and crabs can move more easily, adjusting their positions as necessary. The interactions between these species are shaped by the unique conditions of the vents. Predation happens here, but it often looks different from what we see in shallow waters. Many predators rely on slow, careful movements because rapid bursts of speed can be risky near hot vent openings. The boundary between safe and unsafe temperatures is narrow, and an animal that moves too quickly in the wrong direction can find itself in water hot enough to cause serious damage. This creates a cautious kind of food web, one where each species must balance its need for nutrition with its need for safety. Competition is also present, especially among species that rely on similar chemical gradients. Tube worms may grow so densely that they limit space for newcomers. Mussel beds can expand to cover rocks used by other species. Shrimp swarms shift and compress depending on where the most favourable conditions are. These interactions shape the structure of the community, creating patterns that change over time as the vent's chemistry and flow evolve. Microscopic organisms form a foundation that supports everything else, and the diversity within this microbial world is astonishing. Some species live inside animals, while others form mats or cling to rocks. Some tolerate extremely high temperatures, thriving in conditions that would destroy most known forms of life. Others prefer cooler areas on the outskirts of the vent. These microbes perform chemosynthesis with remarkable efficiency, turning sulfur, methane, or other chemicals into energy that fuels the larger organisms. Their presence shows how deeply interconnected the community is. Without these bacteria and archaea, none of the other creatures could survive in this environment. The more we examine the organisms around the vents, the clearer it becomes that each one contributes to the stability and growth of the community. Tube worms provide structure and surfaces for smaller organisms. Mussels filter particles and help moderate water flow in localized areas. Crabs and shrimp influence microbial growth through their feeding behaviors. Fish contribute to the breakdown of organic material. Together, these species form a network that functions regardless of the absence of sunlight. What stands out most is how well these organisms tolerate conditions that seem unlivable by ordinary standards. They handle extreme heat, high pressure, toxic chemicals, and sudden changes in their environment. Their bodies are built to withstand fluctuations that would strain or destroy shallow water species. The more we learn about them, the more they challenge our ideas about what life requires. These vents show us that life doesn't need light, oxygen, or stable temperatures to thrive. It needs energy, structure, and the ability to adapt to changes. Each organism here has found a way to use what the environment provides. The tube worms convert chemicals through their symbiotic bacteria. The mussels combine filtering with chemosynthesis. The crabs and shrimp take advantage of the abundant microbes. The fish feed on smaller animals and drifting particles. Every species has carved a niche from the shifting, heated landscape. There is still much to observe about how these organisms behave over time, how they respond to changes in vent activity, and how they maintain such dense populations in an environment with so many extremes. But staying here for now, with the heat rising from the chimneys and the creatures moving through the cloudy plumes, offers a clear picture of how life finds a way to flourish, even in places that seem unlikely at first glance. We'll continue exploring these communities, staying close to the details of how they function and how they depend on the forces shaping the vents. There's more to uncover about the chemistry that fuels them, the ways they grow, and the processes that allow them to keep going as the vents around them shift and evolve. When we spend enough time around the vents, it becomes impossible to ignore the fact that everything happening here relies on a type of energy conversion that feels unfamiliar to us. We're used to sunlight being at the centre of most natural processes. Plants depend on it. Animals eat the plants. Predators eat the animals. Even the food chains in the ocean surface depend on light filtering through the water. But in the depths where the vents operate, sunlight never arrives. Photosynthesis can't happen. No sun warms the water or sets daily rhythms. Life goes on anyway, and it does so using chemistry instead of light, relying on reactions that convert the minerals in the vent fluid into usable energy. This process is called chemosynthesis, and while the word might sound technical, the idea behind it is straightforward. Certain microbes have the ability to take chemicals like hydrogen sulfide, methane, or and convert them into organic molecules. These molecules become the fuel that keeps the microorganisms alive, and because these microbes multiply and grow in dense colonies, they become the primary energy source for the larger organisms in the vent community. In the same way that plants anchor food webs at the surface, chemosynthetic microbes anchor food webs around the vents. To understand why this process is so important, it helps to think about the flow of energy. At the surface, energy arrives from the sun. Plants absorb it and turn it into sugars. Animals eat the plants. Other animals eat those animals. Everything depends on the initial step. Here, though, there is no surface and no sun, so the microbes take the role of plants. Instead of sunlight, they rely on chemicals that spill out of the vents. Instead of chlorophyll, they use enzymes specialized to break apart molecules and capture the energy stored in their bonds. Instead of releasing oxygen, they often release sulfur or other byproducts. It's a food web shaped entirely by geology rather than sunlight. The vents release a mixture of compounds, but hydrogen sulfide is one of the most important for chemosynthesis. At the surface, hydrogen sulfide is dangerous. It smells like rotten eggs and can cause serious harm in high concentrations. But down here, in the deep sea, microbes treat it as nourishment. They absorb it, oxidize it, and use the energy released to create organic material. It's a remarkable reversal of perspective. What seems harmful in one environment becomes essential in another. The bacteria don't just float freely in the water, though some species do. Many attach themselves to surfaces, forming mats that ripple with the movement of the currents. Others settle into cracks or coat the outer layers of the chimneys. Some become internal partners for larger organisms, forming symbiotic relationships that are so complete that neither species can survive without the other. These partnerships are some of the most intriguing aspects of life around the vents. They show how deeply intertwined biology and chemistry become in this environment. The tube worms rely entirely on the bacteria living inside them. Their plumes draw in hydrogen, sulfide, and oxygen. Their circulatory systems transport these chemicals to an internal organ where the bacteria live. The bacteria convert the chemicals into sugars. The worms absorb the nutrients directly into their bodies. Without these bacteria, the worms would starve. Without the worms, the bacteria wouldn't have a protected space with a steady supply of chemicals. Both benefit from the arrangement and both are shaped by it. Mussels develop similar relationships. Their gills house bacteria that perform chemosynthesis. The mussels filter water in the usual way, gathering particles, but the bacteria provide an additional source of nourishment. This dual strategy helps the mussels survive when conditions shift. If chemical levels drop temporarily, they can still feed on particles drifting through the water. If particles are scarce, the bacteria help fill the gap. This flexibility gives mussels an advantage in an environment that changes constantly. Shrimp have their own approach. Some species collect bacteria on their mouth parts or within specialized structures on their bodies. They move into areas with higher concentrations of chemicals to allow the bacteria to grow, then scrape or filter them for food. In this way, the shrimp farm their own supply of nutrients. They position themselves carefully along temperature gradients, ensuring that the bacteria receive enough heat and chemicals without exposing themselves to dangerous temperatures. Crabs take advantage of the abundance of organisms fueled by chemosynthesis. They act as scavengers and hunters, feeding on microbes, small animals, and leftover fragments. Their diet is varied, but everything they consume ultimately traces back to the microbes. Even the fish living near the vents rely indirectly on chemosynthesis, feeding on smaller creatures that feed on the microbes or the animals supported by them. it becomes clear that the entire community depends on the initial chemical reactions happening inside the bacteria. The environment around the vents is shaped by these chemical processes. The microbes themselves influence how minerals accumulate on the chimneys. They create layers of organic material that mix with mineral deposits. They alter the flow of nutrients through the ecosystem. They provide food for organisms at every level of the food web. Without them, the vents would be geological features without significant biological activity. The presence of chemosynthesis transforms them into thriving ecosystems. These chemical processes are not simple or uniform. Different microbes use different pathways. Some thrive in hotter water closer to the vent openings. Others prefer cooler areas slightly removed from the heat. Some use hydrogen sulfide. Others rely on methane, iron, or even hydrogen gas. The diversity of chemical pathways reflects the diversity of conditions around the vents. No single reaction can support every species. Instead, a mosaic of chemical processes creates a stable foundation for a wide range of organisms. The vents create sharp boundaries between different chemical zones. Water just outside the vent may contain high concentrations of hydrogen sulfide. A few centimeters farther away, the levels drop sharply. Microbes adapted to high concentrations flourish near the vent openings. Those adapted to lower concentrations thrive farther out. This layering of microbial communities creates a gradual transition in the ecosystem. Larger organisms follow suit, positioning themselves in zones where the microbes they rely on are most abundant. The reactions powering chemosynthesis are driven not only by the presence of chemicals, but also by the absence of oxygen. The deep-sea environment near vents contains oxygen only in limited amounts, delivered by deep currents that mix water from the surface. The microbes take advantage of these low oxygen conditions, using chemical pathways that would be inefficient or impossible in surface environments. These pathways allow them to extract energy from molecules that remain stable in more oxygen-rich waters. Many of the microbes found here belong to groups that are ancient in evolutionary terms. Some are considered among the earliest forms of life based on genetic analysis. Their reliance on chemical energy rather than sunlight suggests that early Earth may have supported similar ecosystems long before photosynthesis evolved. The vents today may resemble the environments where life first emerged, using heat and chemical gradients rather than sunlight as the source of energy. This connection between vent microbes and early life opens up intriguing possibilities. If life began in environments like these, then the ability to harness chemical energy could have been central to the earlier stages of evolution. The vents provide steady sources of heat and chemicals. They offer protected spaces where organic molecules can accumulate. They create gradients that drive chemical reactions. These features make them appealing candidates for the origin of life. Researchers continue to study vent microbes to understand how primitive chemical processes might have evolved into the complex systems seen today. The adaptability of these microbes also raises questions about life beyond Earth. Moons like Europa and Enceladus have oceans beneath their icy surfaces. These oceans may contain hydrothermal vents similar to those on Earth. If chemosynthesis can support ecosystems here, it may be possible for similar processes to support life elsewhere. The presence of chemical energy in these environments could make them suitable habitats even in the absence of sunlight. This possibility has driven significant interest in exploring such moons with future missions. For now, though, staying focused on the vents here on Earth reveals countless details worth exploring. The way microbes attach to surfaces is one example. They form biofilms that grow in layers, each layer hosting slightly different conditions. The outer layers may experience cooler temperatures and lower chemical concentrations, while the inner layers face more extreme conditions. These biofilms create microenvironments that support different microbial species. In some cases, the microbes share metabolic tasks, with one species breaking down a chemical into a form that another species can use. These interactions are part of what makes the vent communities resilient. When conditions shift, the microbes can adjust quickly. Their rapid reproduction rates allow populations to expand or contract, in response to changes in chemical availability or temperature. This flexibility helps maintain stability in the ecosystem. Larger organisms, in turn, depend on the reliability of these microbial processes. If the microbes falter, the entire community feels the impact. Chemosynthesis may seem like an obscure process, but it plays a significant role in global cycles. The vents release metals and minerals into the ocean. Some of these minerals are carried away by currents and influence nutrient availability in distant regions. Microbes around the vents contribute to the breakdown and transformation of these minerals. They participate in the cycling of sulfur, carbon, and other elements. Their activity connects the deep ocean to broader Earth systems in ways that scientists continue to investigate. The more we watch the microbes at work, the clearer it becomes that they are not passive components of the environment. They actively shape it. They create structure. They influence water chemistry. They provide stability for larger organisms. They represent a way of living that depends entirely on chemical reactions deep beneath the ocean's surface. And while these processes might seem foreign, they reveal how adaptable and inventive life can be when placed in unusual conditions. Spending time with these reactions and the organisms that depend on them offers a new perspective on how ecosystems function. It becomes clear that life doesn't require sunlight. It requires energy, and energy can come from various sources. The vents provide a steady supply of heat and chemicals. The microbes convert that energy into usable forms. The larger organisms rely on the microbes. Together they form a community that thrives in darkness, pressure, and isolation. There is still more to understand about how these chemical processes support life, how different species cooperate or compete, and how the entire system responds to shifts in vent activity. We'll continue moving through these details, staying close to the ways that chemistry, heat, and biology come together in this environment. When we take a closer look at the relationships that sustain life around the vents, it becomes clear that almost nothing here survives on its own. Every creature, from the smallest microbe to the largest worm, relies on a partnership that allows it to cope with the heat, the chemicals, and the absence of sunlight. These partnerships are not simple or superficial. They're deeply rooted, often built into the bodies and behaviours of the organisms themselves, to the point where separating one partner from the other would mean the end of both. In a place that seems completely unsuitable for life, life has found ways to build systems of cooperation so integrated that they blur the line between individual and community. The tube worms are one of the clearest examples. Their entire biology is built around symbiosis with chemosynthetic bacteria. Without these bacteria, the worms would have no way to feed themselves. They have no mouths, no stomachs, and no digestive tracts. Instead, they allow the bacteria inside their bodies to perform all the necessary steps of converting chemicals into energy. The worms provide a safe environment with a steady supply of hydrogen sulfide and oxygen. The bacteria handle the rest. This arrangement is so complete that the worms cannot survive anywhere else. If removed from the vent environment or separated from their bacteria, they would quickly weaken. This kind of relationship is not unusual here. Many organisms have evolved similar strategies, each one tailored to the specific conditions of the vents. Mussels host bacteria inside their gills. The bacteria process the chemicals in the vent water, providing nutrients for the mussels. In return, the mussels filter water and offer a stable home for the bacteria to grow. Shrimp keep bacterial colonies on their bodies or within specialized mouth parts, farming them by moving into areas where the chemicals are more abundant. They shift position constantly, allowing the bacteria to grow under the right conditions. They then graze on the bacteria when the colonies become dense. There are fish that carry internal microbial partners and snails with bacteria housed in their tissues. Some microbes live inside the very cells of their larger hosts, forming partnerships so deep that they can no longer survive independently. These relationships are not temporary or optional, they're essential. The vents have created an environment where life is only possible through collaboration. The chemical conditions of the vents encourage these partnerships, Hydrogen sulfide and other compounds provide plenty of energy, but they're also toxic. Many large animals cannot safely process these chemicals on their own. They depend on microbes to transform them into usable forms. The microbes in turn need a consistent supply of the chemicals and a reliable home where they are protected from environmental fluctuations. The result is a setup where each partner fills a role that the other cannot. This interdependence creates stability in an environment that is anything but stable. The vents shift, the chemistry changes, the temperature rises and falls over short distances, but as long as the organisms maintain their partnerships, they can adapt to these shifts. The microbes reproduce quickly, allowing them to adjust rapidly. The larger organisms position themselves along chemical gradients, moving slowly or growing in patterns that keep them within suitable conditions. The partnerships act as buffers, smoothing out some of the volatility of the vent environment. One of the most remarkable examples of this cooperation is found in the way tube worms obtain their bacterial partners. When the worms first settle as larvae, they do not yet have bacteria inside them. They find a spot near a vent, attach themselves to a surface, and then wait for the bacteria to enter through their plume. Once the bacteria are inside, they multiply and fill a special internal organ called the trophosome. The worm's body undergoes major changes during this process, losing its digestive system entirely and becoming dependent on the bacteria. This transformation is irreversible. Once the bacteria take root, the worm becomes fully specialized for life around the vents. Mussels also acquire their bacterial partners early in life. The bacteria enter through the gills and establish themselves in specialized cells. These bacteria don't just sit passively. They divide, adjust to changes in the environment, and respond to fluctuations in chemical availability. The mussel benefits from this flexibility. When chemicals are abundant, the bacteria grow more quickly, providing more nutrients. When chemicals drop, the mussel supplements its diet by filtering particles from the water. This combination helps the mussels persist even when conditions shift unexpectedly. Shrimp show a different kind of partnership. Instead of hosting bacteria inside their bodies, many species allow the bacteria to grow on their exoskeleton or in areas near their mouths. The shrimp move into warm water rich in chemicals, allowing the bacteria to flourish. They then use their limbs to scrape or filter the bacteria for food. This behavior is an ongoing cycle. Shrimp constantly reposition themselves to maintain bacterial growth, almost like tending a garden in a place where gardens shouldn't exist. Their movements, often guided by temperature and chemical gradients, ensure that the bacteria receive the right conditions to grow. These relationships are not always perfect or peaceful. Sometimes the balance shifts in ways that strain the partnership. If chemical levels drop too low, the microbes may struggle to produce enough energy. If temperatures rise too high, the microbes may die off, leaving their host without food. If new vents form nearby, microbial communities may shift their populations quickly, leaving some hosts temporarily disadvantaged. But despite these challenges, the partnerships persist. Evolution has shaped them so thoroughly that the organisms are adapted to cooperate under a wide variety of conditions. The interactions go beyond simple nutrient exchange. Some organisms rely on bacteria that help them tolerate high temperatures or reduce the toxicity of certain chemicals. Others depend on microbes that produce compounds to deter predators or inhibit competing species. Some bacteria detoxify the surrounding environment, stabilizing the chemistry enough for other organisms to settle. The community is threaded together by dozens of such interactions. Each species influences the others, directly or indirectly. There are even examples of cooperation between animals themselves. Mussel beds provide structure that helps other species settle. Tubeworm clusters create currents and sheltered pockets where smaller organisms can hide. When vents collapse or shift, some animals temporarily share space near new openings until the community reorganizes. These interactions aren't cooperative in the sense of intentional teamwork, but they create effects that benefit multiple species. The overall environment becomes more supportive of diverse life because of how each organism fits into the system. Microbial diversity plays a major role in shaping these relationships. Different microbes specialize in different tasks. Some oxidize hydrogen sulfide, others process methane, some break down iron, others convert carbon compounds. These microbes may live side by side in dense mats or layered structures. They may inhabit different parts of the chimneys or different tissues of the animals. This variety ensures that the environment continues to function even when conditions shift. If one chemical becomes scarce, another pathway may take prominence. If temperatures change, heat-tolerant microbes may become more influential. This adaptability is essential because the vents do not remain constant. A shift in the flow of vent fluid can alter the chemical composition of the surrounding water. A collapse of a chimney can redirect the flow. A buildup of minerals can block an opening. Each of these changes affects the microbial community first. The microbes respond quickly, adjusting their populations and chemical pathways. The larger organisms then follow, changing their positions, modifying their feeding behaviours, or relying more heavily on certain microbial partners. The system absorbs the changes because the cooperation runs deep. These relationships also shape how new communities form. When a vent opens in a previously inactive area, microbes arrive almost immediately. Some drift in the water, others are released from cracks in the crust. As soon as the chemicals are available, the microbes begin their work. Their growth attracts the larvae of larger organisms. Tube worm larvae settle first, followed by mussels, shrimp and other species. The partnerships begin anew. The microbes colonize the tissues of the animals, and the animals stabilize the environment, creating new surfaces and altering water flow. Within months, a thriving community can emerge. The formation of these communities highlights another aspect of symbiosis: connectivity. The deep sea may seem isolated, but life here spreads through networks. Larvae drift for long distances, guided by chemical cues. Microbes disperse through water currents or travel with larger organisms. When vents shut down or collapse, the species move gradually toward other active vents. These movements maintain genetic exchange between populations, ensuring that the partnerships remain resilient and diverse. The depth of these relationships becomes even more apparent when we consider what happens when vents shut down. Without the chemical reactions that power chemosynthesis, the microbes decline. The larger organisms lose their food sources. Some species, like mussels, may survive for a time by relying on alternative feeding strategies. Others, like tube worms, quickly deteriorate. The entire community shifts as animals move away or die off. But when a new vent opens nearby, the process begins again. New partnerships form. Microbes colonize the area. Larvae settle. The cycle continues. This cycle reveals something important about symbiosis here. It's not just a strategy for surviving in the present, it's a strategy for enduring change. The vents can be unpredictable. They can shift, vanish, or appear with little warning. The organisms that rely on them have adapted to a lifestyle where everything could transform at any moment. Their partnerships provide stability in the midst of geological activity. These forms of cooperation also give insight into how life can thrive in extreme environments. If organisms can build entire ecosystems around chemical energy, then the potential for life in other harsh environments becomes more plausible. The symbioses show that life doesn't need gentle surroundings. It needs opportunities to connect. When chemical energy is available, life finds ways to harness it. When conditions change, life finds ways to adapt. The more we examine these partnerships, the more evident it becomes that no organism here is truly alone. Every creature is tied to another, either directly through symbiosis or indirectly through shared dependence on the microbes. The community functions as a network that balances heat, chemistry, and pressure. Each organism fills a role shaped by cooperation. There is more to explore about how these relationships influence the structure of the vents, how the organisms communicate chemically, and how the community changes as vents evolve. We will keep moving through these details, staying centered on the ways life holds itself together in a place that seems, at first glance, wholly unsuitable for survival. When we think about the creatures that live near the vents, it becomes natural to wonder how their bodies manage to function under such harsh conditions. Most animals on the surface have delicate systems that depend on narrow ranges of temperature, pressure, and chemistry. Even small deviations can cause stress or damage. Yet the organisms thriving near the vents have evolved structures and physiological strategies that allow them to handle pressures hundreds of times greater than what we experience. Temperatures that shift from freezing to nearly boiling in a matter of centimetres. Chemicals that would poison most known life, and complete darkness that forces them to rely on senses other than vision. The architecture of these extremophiles, from the smallest microbes to the largest animals in the community, is shaped by forces that push the limits of biological possibility. If we start with the microbes, the most fundamental extremophiles in this environment, their adaptations become a foundation for understanding everything else. Many of these microorganisms belong to groups that have been evolving for billions of years. Their cell membranes contain specialized lipids that remain stable under extreme pressure and heat. Their proteins are shaped in ways that prevent them from unfolding, even when temperatures rise close to the boiling point of water. Some enzymes that would denature in more moderate environments remain functional at temperatures around 120 degrees Celsius. Their genetic machinery includes repair systems that activate quickly if molecules become damaged. These microbes also adjust their internal chemistry to maintain stability, balancing salts, ions, and other components so that their cellular processes continue smoothly even when external conditions swing dramatically. These adaptations give the microbes remarkable resilience. Some species thrive directly inside the vent openings, where the water is far too hot for larger organisms. Others move outward, forming layers that shift in composition as temperatures and chemical concentrations change. This gradient of microbial life creates a zone where each species occupies the conditions it can tolerate best. The microbes don't just endure the environment, they make use of it. They rely on the heat to power certain reactions. They use the pressure to maintain the structure of their proteins. They take advantage of the chemical availability to fuel metabolism. Their architecture is built for extremes from the ground up. The larger organisms, such as tube worms, mussels, shrimp, and crabs, also exhibit significant adaptations, though their solutions are more complex because their bodies are composed of many interacting systems. Tube worms, for example, construct rigid tubes from chitin-like materials that provide protection from predators, pressure changes, and shifting currents. These tubes insulate the worms from sudden bursts of extremely hot water and create stable microenvironments where the worm's exposed plume can safely collect chemicals from the water. The worm's plume is a finely tuned structure. It contains millions of tiny blood vessels that maximize contact with the surrounding water. Its bright red color reflects the presence of large quantities of hemoglobin, modified to carry both oxygen and hydrogen sulfide. These two chemicals would normally be incompatible. Hydrogen sulfide binds to hemoglobin and blocks oxygen transport in humans and most other animals. But tube worms have evolved molecules that prevent the sulfide from causing harm. Their unique adaptations allow them to transport both substances at once, delivering them safely to the bacteria inside their bodies. This arrangement provides the bacteria with the exhaust of the vents, while also providing the worm with oxygen from the surrounding seawater. Inside the worm, the trophosome houses the bacteria and creates an environment where they can thrive. This organ is composed of thousands of lobes filled with microbial cells supported by the worm's circulatory system. The worm's blood carries oxygen and sulfide to the bacteria, while the bacteria produce compounds the worm can use. The partitioning of these processes requires precise control. Specialized hemoglobin molecules protect the worm from the toxicity of sulfide. An internal membrane separates the bacteria from the rest of the worm's tissues. The architecture of the tube worm is essentially a scaffold built around its microbial partners, with every part of its internal organisation serving to maintain that relationship. Mussels have their own structural innovations. Their shells are thicker and sturdier than those of many shallow water species, helping them withstand the weight of water pressing down from above. The tissues inside their shells contain pockets where chemosynthetic bacteria live. These pockets provide stable environments where the bacteria can process chemicals from the water. The mussels adjust the flow of water across their gills to regulate how much oxygen and hydrogen sulfide reach the bacteria. Their filtration systems are tuned to the chemistry of the vent environment, allowing them to extract particles while also nourishing their internal partners. The combination of filtering and chemosynthesis gives them a versatile approach to feeding. Shrimp show another set of adaptations. Some species have light-sensing organs on their backs or near their mouths that detect faint infrared radiation emitted by the vents. These organs are not eyes in the traditional sense, but they allow the shrimp to find safe zones where temperatures are ideal for the bacteria they farm. Their exoskeletons are built to withstand rapid temperature changes, and their gill structures help them regulate exposure to chemicals. Their behaviours are tightly linked to their structural adaptations. They move into warmer water when bacterial growth is needed, then move into cooler areas when the heat becomes dangerous. Their bodies are shaped for rapid adjustments, with limbs and sensory organs tuned to chemical cues rather than visual ones. Crabs in the vent environment display adaptations that reflect both the physical challenges of the deep sea and the chemical challenges of the vents. Their exoskeletons are often pale because pigmentation offers no benefit in darkness. Their claws and legs are shaped to grass surfaces around the chimneys, allowing them to climb over uneven mineral deposits. Some species have specialised hairs or bristles on their limbs that collect bacteria from the water. Their metabolism functions at low temperatures, but they can briefly withstand higher temperatures when necessary. Their sensory systems rely on chemical cues rather than light, and their internal organs are adapted to process small amounts of toxic substances without harm. Fish near the vents are not as heavily modified as the smaller creatures, but they still show structural adaptations that allow them to handle the high pressure and limited food availability. Their muscles contain proteins that remain flexible under intense pressure. Their bones are less dense, reducing the risk of fractures. Their metabolisms are slow, conserving energy in the cold water surrounding the vents. They rely heavily on detecting movements and vibrations, using lateral line systems and other sensory structures to navigate the darkness. Although they don't rely directly on chemosynthesis, they've adapted to integrate into the food web built on microbial energy. When we shift our focus from individual organisms to the entire community, the structural complexity becomes even more apparent. The organisms do not simply exist side by side, they create and shape their environment. Tube worm clusters alter water flow, creating sheltered pockets where smaller organisms can settle. Mussel beds provide surfaces for microbes to attach to and create stability in areas where sediments would otherwise shift. Shrimp swarms form moving layers that influence the distribution of microbial mats. Even the presence of predators such as certain fish or crabs impacts where smaller animals gather and how they position themselves around the chimneys. The vents themselves become part of this architectural framework. As chimneys grow or collapse, the living community reorganises. New mineral surfaces provide fresh areas for microbial colonisation. Openings in the chimneys create new sources of heat and chemicals. When vents shut down, the organisms retreat or disperse, leaving behind structures that influence the next wave of settlers. The architecture of the extremophiles here is not just biological, it is ecological and geological as well. The interactions between organisms also shape their physical structures. For example, some tube worms grow longer when competing for space, stretching upward to catch more chemical-rich water. Mussel beds may thicken in areas where they face competition from shrimp or other mussels. The architecture of each species adjusts in response to the community around it. These adjustments, while subtle on short time scales, become significant over months or years. shaping the physical landscape of the vent field. One of the most surprising aspects of these extremophiles is their ability to maintain internal stability despite the instability of their surroundings. Their bodies employ mechanisms that protect against rapid temperature changes, such as heat shock proteins that repair damage. Their membranes remain flexible under pressure. Their DNA repair systems are robust, allowing them to fix damage caused by reactive chemicals. These internal features allow them to maintain a steady physiological state, even when the external environment fluctuates wildly. The microbes demonstrate this resilience especially clearly. Some species can survive temperatures far above what we consider normal for life. Others function under extremely low oxygen conditions. Some thrive in acidity that would dissolve the tissues of most animals. Their enzymes are stable in extremes of pressure and temperature. Their genes are expressed differently depending on the availability of chemicals. Their membranes adjust to changes in salinity or pH. They are built to respond swiftly to new conditions. This adaptability at the microbial level influences the evolution of the larger organisms. Tube worms couldn't survive without bacteria capable of processing sulfide. Mussels rely on bacteria that can handle both chemical scarcity and abundance. Shrimp depend on bacteria that grow rapidly under fluctuating temperatures. The microbes drive the architecture of the entire ecosystem. Their flexibility allows the larger organisms to evolve structures tailored to the microbial needs. The result is a community where biological architecture is a shared construction rather than the product of any one species. While each organism has its own design, the overall architectural theme is one of efficiency and resilience. Nothing is wasted. Every adaptation has a purpose shaped by the environment. The extremophiles here are not just creatures surviving in harsh conditions. They are creatures built for collaboration, for optimization, for making use of every available resource. Their bodies and behaviors reflect the demands of the vents and the opportunities the vents provide. There is much more happening beneath the surface of these adaptations. The biochemical pathways that allow chemosynthesis to function, the structural features that protect organisms from heat and pressure, and the sensory strategies that allow animals to navigate darkness all contribute to an environment that operates on principles very different from those we see at the surface. We'll continue moving through these details, following the ways these organisms interact with the forces around them and how their structures reveal the unique demands of life in this part of the ocean. When we spend enough time imagining the communities around the vents, it becomes necessary to step back and consider the forces beneath them, the forces that create these openings in the first place. Every vent owes its existence to movements deep inside the earth, movements that happen far below the seafloor where heat, pressure, and molten rock interact in ways that reshape the crust over time. The Earth is not a still or quiet planet. Far from being a rigid sphere, it's more like a layered machine that never stops shifting. The surface feels solid under our feet, but underneath that solidness are slow, constant motions that create cracks, ridges, and openings where heat escapes. The vents, with their chimneys and plumes, are one of the most visible results of these hidden processes. The seafloor where black smokers are found is usually located along mid-ocean ridges. These ridges stretch across entire oceans, forming long, winding boundaries where tectonic plates separate from each other. It may sound dramatic to imagine the surface of the Earth splitting apart, but these separations happen gradually. The plates move only a few centimeters each year, slower than fingernails grow. Over long periods, though, these small movements add up. As the plates pull away from each other, new crust forms from magma rising from below. The magma cools and hardens, pushing older crust aside. This process creates a continuous conveyor belt that reshapes the ocean floor. When tectonic plates separate, cracks develop in the crust. Seawater, cold and dense, seeps into these cracks through tiny openings. It travels downward until it reaches areas heated by nearby magma. The heat increases dramatically, transforming the water into a superheated fluid capable of dissolving minerals from the surrounding rocks. This process creates the mineral-rich fluid that eventually becomes the vent plume when it rises back to the surface. This entire system depends on the cracks and openings created by tectonic activity. Without these openings, the water wouldn't reach the hot rock below. Without the heat, the water wouldn't dissolve the minerals. Without the dissolved minerals, the chimneys wouldn't form. And without the chimneys, the communities of organisms wouldn't develop. Everything starts with the moment when the Earth's crust breaks, just enough to allow the water to flow downward. The process is not violent in the way we might imagine earthquakes on land. Most of the time, these shifts are subtle and continuous, but there are moments when the motion becomes more intense, causing small quakes that ripple through the sea floor. These quakes don't necessarily create destruction the way large earthquakes do at the surface, but they can alter the positions of vents, open new cracks, or close old ones. The organisms living nearby may sense these changes through tiny vibrations or sudden shifts in temperature or chemistry. Their environment can change before they even have time to react fully, though their adaptations help buffer some of these disturbances. The heat beneath the vents comes from magma chambers deep within the crust. These chambers are pockets of molten rock that supply the warmth necessary to drive hydrothermal circulation. Magma may rise closer to the surface in some areas and remain deeper in others, creating variations in how hot the vent fluid becomes. In some places, vents release clear, superheated water rich in minerals. In others, the water reacts with different parts of the crust and emerges with distinct chemical signatures. These differences help determine which organisms thrive at each vent site. Heat also plays a role in creating gradients along the sea floor. The areas closest to the vent openings are the hottest, with water temperatures far above what most organisms can tolerate. Just a few centimetres away, the temperature drops sharply, creating narrow zones where life can exist. The cracks beneath the vent influence how the heat spreads, shaping the geometry of the ecosystem on the surface. Minerals within the crust also influence the chemical composition of the vent fluid. When the water travels through cracks, it dissolves sulfur, iron, copper, and other elements. The specific combination depends on the geology of the region. Some vents produce fluid rich in hydrogen sulfide, which supports chemosynthetic bacteria. Others release methane or metals. These differences create variations in the communities that form around the vents. Even vents only a few meters apart may host slightly different sets of organisms because of the chemistry supplied by the cracks below. The creation of these cracks is not a one-time event. The crust is constantly moving and adjusting. New cracks form while old ones seal. Magma rises and cools. Pressure builds and releases. The vents can shift position, form clusters, or disappear altogether. Some vents remain active for years or decades. Others last only a short time before shutting down. The entire environment operates on timescales tied to tectonic motion, heat flow, and mineral deposition. This constant change shapes the behaviour of the organisms that depend on the vents. Larvae travelling through the water must find suitable chemical signals to settle near active vents. Tube worms cluster where sulfide is abundant. Mussels settle where the chemistry aligns with their bacterial partners. Shrimp move repeatedly, responding to subtle shifts in temperature and chemical availability. Every creature in the area senses the effects of the Earth's movement, even if they do so indirectly. The geometry of the cracks also affects water flow. Fluid rises through channels that vary in width, shape, and angle. Some channels narrow and focus the flow, creating high-speed jets of mineral-rich water. Others widen, allowing the fluid to spread slowly. These differences influence how the chimneys grow. A strong, fast flow tends to build tall, narrow chimneys. A slower flow may produce wider, more irregular structures. The architecture above the seafloor reflects the structures hidden below it. The cracks themselves form from a combination of tension and heat. As the tectonic plates pull apart, the crust becomes thinner. Thinner crust is more likely to break. The heat from below causes expansion, which stresses the crust further. Over time, the combined forces create pathways from the hot rock to the ocean floor. These pathways are rarely straight. They twist and intersect, creating networks that guide the flow of water. The result is a series of channels that function like a natural plumbing system. This plumbing system is constantly tested by shifting pressure and temperature. Sometimes clogs form within the channels when minerals accumulate faster than they can be flushed out. When this happens, the vent flow slows or stops entirely. Pressure builds behind the blockage until it finds a new path, opening a fresh crack somewhere nearby. The organisms living on the surface may experience sudden changes in the availability of chemicals. A once thriving patch of tube worms might find itself cut off from its source of nutrients. Just a few meters away, a new vent might open, releasing a fresh supply of heat and chemicals that attracts larvae and kickstarts a new community. The plumbing system beneath the vents demonstrates just how dynamic the seafloor can be. Even in an environment where everything appears still from our perspective, geological forces continue to act. The heat flow from the mantle, the movement of tectonic plates, and the slow but persistent formation of cracks all contribute to the life above. It may look quiet and permanent, but the reality is a deep system in motion. The pressure at these depths plays a role too. The immense weight of the water above affects how the cracks form and how the fluid moves. High pressure allows water to become superheated without boiling. This superheated water dissolves minerals more effectively. If the pressure were lower, the water would boil before it could reach the temperatures needed to dissolve sulfides. The vents wouldn't function in the same way. The organisms depending on them wouldn't exist. Pressure becomes one of the factors that make these ecosystems possible. The seafloor also contains ridges, fissures, and valleys shaped by the movement of the plates. These features influence how the vent fluid spreads after it exits the chimneys. Some areas channel the fluid upward, others allow it to drift sideways. The landscape, shaped by geological forces, becomes another part of the system that organisms must navigate. Tube worms may anchor themselves on raised ridges. Mussels may cluster in sheltered pockets. Shrimp may gather on slopes where the vent fluid spreads in thin sheets. The creatures respond not just to the chemicals and heat, but to the structure of the ground beneath them. Chemical reactions in the crust also contribute to the creation of the vents. When seawater reacts with certain minerals, it produces heat. This heat adds to the thermal energy from the magma, increasing the temperature of the fluid. The combination of chemical heat and geothermal heat drives the movement of the water through the cracks. The reactions also change the composition of the fluid, adding elements that bacteria can use for chemosynthesis. These processes create an environment where chemistry, heat, and geology overlap in ways that support life. The vents are also part of a larger network spanning the entire ocean floor. Mid-ocean ridges circle the planet, forming the longest mountain chains on Earth. Hydrothermal vents occur at many points along these ridges. Each vent field is a piece of a global system that influences the chemistry of the oceans. The minerals released by the vents can travel long distances. Some contribute to nutrient cycles in distant areas. Some settle to the ocean floor, creating deposits studied by geologists. The vents play a role in shaping the marine environment far beyond their immediate surroundings. Even though these vents are formed by deep, powerful forces, they operate on scales that directly affect the organisms living on them. A shift in the crust might open a new vent, closing another. A crack might expand, altering the flow of water. A chimney might collapse, reshaping the habitat for dozens of species. The creatures near the vents must adapt to these changes as they happen, guided by instincts and behaviours shaped over millions of years. These geological forces also influence the evolutionary history of the vent organisms. Periods of increased tectonic activity may create more vents, providing opportunities for species expansion. Periods of decreased activity may reduce the number of vents, leading to more competition and selective pressure. Over time, these cycles shape the genetic diversity of the organisms. They create opportunities for new adaptations to develop, especially among the microbes that respond quickly to chemical changes. When we think about all of these processes together, it becomes clear that the vents are not isolated features. They are the result of continuous interactions between the Earth's interior and the water above it. The cracks form because the crust moves. The heat flows because the mantle is active. The minerals dissolve because the temperature and pressure allow it. The organisms thrive because they've evolved to make use of every part of this system. There is still much more to uncover about how the Earth's crust shapes the vents, how the vents influence each other across the seafloor, and how the organisms respond to geological changes. We'll continue moving through these details, staying close to the interplay between the forces beneath the Earth and the life that has adapted to live on top of them. When we look closely at how life survives around the vents, the most remarkable feature isn't simply that organisms can tolerate the heat or the pressure, it's that they can function without sunlight at all. Everything they do, from growing to reproducing to building communities, relies on chemistry instead of light. This shift from light-driven energy to chemical energy is not just a small adjustment. It represents a fundamental alternative to the system that supports nearly all visible life on Earth's surface. To understand the vent communities, we need to follow the flow of chemical energy from the moment it leaves the cracks in the seafloor until it becomes part of the tissues of worms, shrimp, mussels, and the countless other organisms living in this environment. Sunlight powers the food webs on land and in shallow waters. Plants use photons to convert carbon dioxide into sugars. Animals feed on the plants or on other animals, gradually passing the energy upward. That's the familiar pattern. Down here, though, the vents create an entirely different starting point. Instead of photons, the energy arrives in the form of reduced chemicals dissolved in the vent fluid. Hydrogen sulfide is the most important of these chemicals, and it pours out of the vents in concentrations that would be dangerous for surface life. Around the vents, however, hydrogen sulfide becomes the raw material for building biological energy. When microbes oxidize hydrogen sulfide, they release energy, and that energy becomes the foundation for the entire ecosystem. To understand how this works, it helps to think of the chemical bonds in hydrogen sulfide the way we think about sunlight striking a leaf. In photosynthesis, plants take energy from light and store it in the chemical structure of carbon-based molecules. In chemosynthesis, microbes take energy from chemical reactions and store it in the structure of organic compounds. The starting point is different, but the outcome is similar: the creation of a substance that can fuel life. Hydrogen sulfide, methane, hydrogen gas, and iron compounds are some of the molecules used in this process. Different microbes specialize in different reactions. Some microbes oxidize sulfide into sulfate. Others oxidize methane into carbon dioxide. Still others use hydrogen gas as an energy source. The variety of chemical pathways provides flexibility in an environment that changes frequently. If one chemical becomes scarce, microbes can shift toward another, either by altering their behavior or by allowing species better suited to the available chemicals to become more abundant. The reactions behind chemosynthesis often occur in carefully controlled environments within microbial cells. Enzymes facilitate the transfer of electrons, driving the formation of molecules like ATP, which microbes use for energy. The microbes then incorporate carbon from dissolved carbon dioxide into organic compounds, building the sugars, amino acids, and other substances they need. Larger organisms feed on these microbes directly, or partner with them through symbiosis, integrating the microbial processes into their own metabolic systems. Every part of the vent community depends on these chemical reactions. The structure of the vent chimneys influences how efficiently these reactions occur. Chimneys made of sulfides create surfaces with tiny pores and crevices where microbes can attach and form layers. These layers often extend outward from the vent opening in a gradient, with different species positioned at the distances where their preferred conditions exist. For example, microbes that thrive at very high temperatures cluster closest to the vent, where the water is still extremely hot but not quite lethal. Farther from the vent, the temperature drops, and different microbial species become more common. The The chemical concentrations also change with distance. Hydrogen sulfide is abundant near the opening and becomes more diluted farther away. The microbes arrange themselves in response to these gradients. The placement of microbes along these gradients creates a structured environment where chemical energy flows outward from the vent opening. Larger organisms follow these gradients as well. Tube worms anchor themselves in areas where both oxygen and hydrogen sulfide are available in balanced amounts. Mussels settle where the water delivers chemicals at a rate that matches their internal bacterial populations. Shrimp find positions where the temperature is ideal for the bacteria they cultivate. Every creature uses the chemical flow in its own way, guided by the structures and conditions created by the vent. The chemistry of the vent fluid changes as it mixes with seawater. When the hot fluid meets cold water, minerals precipitate out, forming black particles that give the vent fluid its smoky appearance. The precipitation process removes some chemicals from the fluid, but leaves others available for the microbes. The mixing also alters the pH, temperature and oxygen content, creating zones with distinct characteristics. These zones are not static. They shift as the vent's flow changes, as chimneys grow or collapse, or as currents alter the movement of water. This constant change requires microbes and larger organisms to adapt quickly. Microbes respond by adjusting their gene expression or shifting population sizes. Larger organisms adjust their positions or rely on their symbiotic partners to regulate internal chemistry. The entire ecosystem depends on these adjustments. If the flow of chemicals were too unpredictable for microbes to handle, the larger organisms would quickly lose their energy source. But the microbes have evolved to be flexible, allowing the ecosystem to remain stable despite the dynamic nature of the environment. One of the most surprising aspects of this chemical system is how efficient it can be. Chemosynthetic microbes in some locations produce organic material at rates comparable to productive surface ecosystems. This means that even in complete darkness, without any sunlight, the vent communities can grow densely. Tube worm clusters can become thick enough to resemble the crowded vegetation of shallow water ecosystems. Mussel beds can spread across entire sections of the seafloor. Shrimp swarms can become so dense that they obscure the chimneys beneath them. The availability of chemical energy supports these dense populations, creating an abundance of life in a place where we might expect only isolation and scarcity. The efficiency of chemosynthesis is tied to the chemical richness of the vents. Hydrogen sulfide carries a lot of potential energy, and when microbes oxidize it, they release significant amounts of usable energy. The same is true for methane in some vent systems. The combination of heat and pressure ensures that these chemicals remain dissolved in the vent fluid at concentrations that favour rapid microbial growth. This chemistry transforms the vents into oases of energy in an otherwise energy-poor environment. There are also chemical reactions happening inside the organisms themselves that help them tolerate the vent conditions. Tube worms use specialised hemoglobin to transport hydrogen sulfide without being harmed by it. Mussels regulate the flow of chemicals to their internal bacteria by adjusting how they pump water. Shrimp position themselves in ways that maximise the chemical exposure of their bacterial colonies. Crabs rely on microbes attached to their limbs to help them obtain nutrients. The internal chemistry of each organism has evolved to complement the chemical environment outside. The reliability of chemical energy from the vents also influences how quickly organisms can grow. Tube worms are capable of rapid growth under the right conditions, adding several centimetres in short periods. Mussels and shrimp can reproduce quickly when the chemical flow is steady. Microbial populations can expand dramatically when new surfaces appear or when chemical concentrations increase. These bursts of growth allow communities to establish themselves rapidly when new vents open. However, the vents are not always consistent. Their chemistry can change suddenly. A shift in the flow rate may alter the concentrations of hydrogen sulfide. A collapse within the chimney may redirect the fluid, cutting off some organisms from their source of chemicals. The Earth's motion beneath the vents may open new cracks and close old ones. The organisms must respond to these changes. The microbes usually adjust quickly because of their short generation times. The larger animals move, reposition themselves, or rely on the flexibility of their symbiotic partners. When chemical energy declines, the community begins to reorganize. Some organisms stay as long as they can. Others move away. Larvae may drift elsewhere in search of more favorable chemical signals. A vent that once supported a large community may become quiet. But somewhere nearby, a new vent may be forming. The cycle of chemical energy shifts again, beginning the process of microbial colonization and community formation from the start. Chemistry doesn't just influence growth and feeding, it also affects reproduction. Some organisms time their reproductive cycles to changes in chemical flow. Others produce larvae that drift long distances until they detect chemical signatures from active vents. These chemical signals guide the larvae to the right places, ensuring that new generations settle in areas with enough energy to support them. The cues are subtle: slight changes in dissolved molecules, faint gradients in temperature, variations in pH, but the larvae are sensitive enough to detect them. The chemical environment becomes the map the organisms use to navigate the deep sea. The reliance on chemistry over sunlight also affects how vent communities interact with the broader ocean. While surface ecosystems depend on seasonal light cycles, vent ecosystems follow the rhythms of geological activity. Their productivity rises and falls with the flow of chemicals. Their stability depends on the tectonic processes below. This connection ties the biological world to the geological one in a direct, ongoing way. When the Earth breaks open beneath the water, new chemical energy becomes available. When it cools or shifts, the energy disappears. The organisms react accordingly. The broader ocean still influences the vents. Deep currents deliver oxygen that microbes need to complete their chemical reactions. The seawater acts as a solvent, carrying chemicals away and diluting them. Pressure from the water column allows chemical reactions to occur at temperatures that would cause boiling at the surface. These factors ensure that chemistry can substitute for sunlight in a consistent and continuous way. There is still much to understand about the chemical pathways used by vent microbes. Some species use reactions that scientists are only beginning to study. Others have metabolic strategies that blur the lines between known categories. The variety of chemical approaches makes these ecosystems valuable for research. They offer insight into how life can adapt to extreme environments, and how chemistry can serve as the foundation for biological processes in settings that differ dramatically from the world we inhabit on land. The more we explore these chemical systems, the clearer it becomes that life does not depend on sunlight. It depends on energy. That energy can come from photons or from chemical bonds. It can flow through food webs built on plants or through webs built on microbes. As long as energy is available in a usable form, life finds ways to capture it and grow. The vents demonstrate this principle with remarkable clarity. There is more ahead to explore about how these chemical reactions connect to the early history of life, how they influence the evolution of extremophiles, and how similar processes might operate in oceans beyond Earth. We'll move toward those ideas next, keeping close to the details of how chemical energy supports everything in the vent communities and how it shapes the possibilities for life in places far removed from sunlight. When we consider the chemistry, the heat, and the constant motion surrounding the vents, a natural question begins to appear. What do these environments tell us about the world long before there were forests, oceans filled with fish, or continents covered in plants and animals? The black smokers are not just unusual ecosystems in the present day. They also serve as windows into conditions that existed on early Earth, a time when the planet looked and behaved very differently from what we see now. These smoky pillars, with their mineral structures and chemical reactions, may reflect some of the environments where life first gained a foothold. To understand why these vents draw so much attention from researchers studying the origin of life, it's helpful to picture the Earth as it was more than 4 billion years ago. Back then, the surface was much hotter. The crust was thinner and constantly reshaping itself. The atmosphere lacked oxygen. Intense volcanic activity released gases into the air and minerals into the sea. Comets and asteroids struck the surface frequently. Sunlight reached the Earth, but the atmosphere and surface conditions were far less stable. Under these circumstances, life couldn't have depended on gentle environments, mild temperatures, and predictable sources of energy. It needed places where chemical energy could accumulate, where reactions could occur repeatedly, and where conditions could sustain molecules long enough for them to replicate and evolve. The vents, with their steady supply of heat and chemicals, offer exactly this kind of environment. When superheated fluid rises from beneath the seafloor and mixes with cold water, minerals precipitate out and create structures filled with pores, cracks, and microscopic compartments. These compartments can trap molecules, creating spaces where chemical reactions happen repeatedly. The walls of these compartments contain minerals like iron and sulfur, which can catalyze reactions, meaning they can help molecules combine or break apart without being consumed in the process. These catalytic reactions could have played a role in forming the first complex organic compounds. The architecture of the chimneys resembles a natural laboratory. Instead of glass containers and controlled temperatures, the early Earth might have offered mineral chambers, fluctuating heat, and dynamic chemistry produced by the flow of water through rock. These conditions allow for concentration, separation, and recombination of molecules, three processes that are vital for the development of complex chemical systems. When scientists examine the internal textures of fossilized vent structures, they see patterns that suggest a long history of chemical reactions taking place within them. Some structures contain layers of minerals that alternate depending on temperature and chemical availability, showing how conditions could shift over time. These shifts could encourage different chemical reactions at different moments, providing a range of possibilities for early molecules to form and reorganize. It's not difficult to imagine complex organic molecules forming in such a setting. The microbes living near the vents today use chemical pathways that resemble the processes scientists believe existed on early Earth. Many vent-dwelling microbes rely on simple, ancient metabolic reactions. They use hydrogen, sulfur, or iron as energy sources and produce compounds that early life might also have produced. Some of these microbes break down molecules in ways that hint at the earliest biochemical networks. Networks that likely developed long before organisms developed the ability to use sunlight. This resemblance doesn't prove that life began around vents, but it provides a compelling example of how life could function in the absence of sunlight. The vents also create conditions that protect fragile molecules. In open water, molecules can diffuse too quickly to react with each other. But in the narrow spaces within chimney walls, molecules can become concentrated. They stay close enough to interact repeatedly. This repeated interaction increases the chances of forming stable structures, such as short chains of amino acids or nucleic acids. Once these chains form, they can impact the environment around them, influencing which molecules enter or leave the compartment. Over time, more complex networks can develop. Chemical systems that become slightly better at using available resources might persist longer than others. This gradual improvement could form the basis for early evolution. Another factor making vents appealing as early life candidates is the constant supply of energy. Early life would have needed a reliable energy source. Sunlight was available, but in the early oceans it may not have penetrated deeply enough to support widespread photosynthesis. The vents, on the other hand, provide a continuous flow of energy in the form of chemical gradients. These gradients, differences in chemical concentration between the hot vent fluid and the cold seawater, can drive reactions and support growth. The microbes that evolved to use these gradients might resemble the first organisms on Earth. The composition of the vent fluid also supports this idea. Hydrogen gas, for example, is common in many hydrothermal systems. It is an energy-rich molecule that early microorganisms could easily use. Some of the oldest microbial lineages known today rely heavily on hydrogen. These microbes may not be unchanged remnants from early Earth, but they give hints about what the earliest forms of life might have been capable of doing. Minerals like iron and nickel, common in vent structures, can catalyze reactions that produce organic molecules. In laboratory experiments, when water, simple gases and minerals similar to those found in vents are combined under high heat and pressure, organic molecules can form. This doesn't prove that vents created early life, but it shows that the reactions necessary for life can occur under vent-like conditions. The smoky plumes streaming from the chimneys today might resemble the plumes that supported early ecosystems billions of years ago. Chemistry isn't the only clue that vents offer. The physical environment near the vents also resembles conditions thought to exist on early Earth. The heat near the openings provides energy, while the surrounding cold seawater creates steep gradients. These gradients can drive the movement of molecules, sorting them by size or charge. The movement of water through cracks in the rock mimics cycles of heating and cooling that can influence chemical reactions. These cycles encourage molecules to assemble and disassemble, creating opportunities for complexity to emerge. The vents also show how life can persist in isolation. Early Earth may not have had widespread ecosystems. Life may have been confined to isolated pockets. Hydrothermal systems could have been among these pockets. The organisms living at the vents today demonstrate that life can function independently from sunlight, relying on local sources of energy. This independence helps explain how early life might have survived even when the global environment was unstable. Observing present-day vent communities gives scientists models for how early ecosystems could have looked. Microbes grow densely near the openings, forming mats that break down chemicals and release new substances into the water. Larger organisms rely on the microbes, forming simple but functional food webs. On early Earth, similar systems might have formed, though without the larger animals we see today. These systems would have been dominated by microbes, but the structure of the community, organisms clustering near energy sources and forming interconnected networks, might have resembled modern vent ecosystems in basic ways. The vents also reveal how life can adapt to shifting environments. Early Earth experienced frequent changes in temperature, chemistry, and geological activity. Organisms near vents adapt to such changes regularly. When the chemistry shifts, microbial communities reorganize. When a vent opens or closes, new species move in or out. Early life might have been similarly flexible, able to survive in environments where conditions changed rapidly. The vents provide real-world examples of how such adaptability can function on long timescales. Another clue comes from the way vent communities spread. When larvae drift through the ocean, they search for chemical signals that indicate an active vent. When they sense the right combination of heat and chemicals, they settle. Early life may have spread using similar mechanisms, drifting until it encountered environments with the right conditions for growth. This process creates patterns of colonization and migration, with communities forming where energy is abundant and dispersing when conditions decline. This dynamic could resemble the ways life expanded through early oceans. Study of the vents also suggests how life could have spread to other parts of Earth. If life began in one hydrothermal system, it could spread gradually through water currents, carried by simple organisms capable of surviving long journeys. As the Earth cooled and stabilized over millions of years, these organisms could colonize new environments, eventually giving rise to more complex ecosystems. The vents show that life can start in one place and expand outward, even in extreme conditions. There is ongoing debate about whether life began at vents or in other environments, such as tidal pools or shallow water hot springs. The vents don't offer all the answers, and researchers continue to explore multiple possibilities. But the vents provide a compelling case because they offer a combination of energy, chemistry, and structure that seems well suited to the earliest biological processes. They demonstrate a kind of self-sustaining system where chemical reactions, energy flow, and molecular organization occur naturally. These smoky pillars also reveal how life and geology influence each other. The formation of chimneys changes water flow and chemical distribution. Microbes alter the chemistry of the water around them. As life evolves, it affects the minerals deposited in the chimneys. This constant interaction between life and environment reflects how early Earth may have functioned. Life did not simply appear on an inert planet. It emerged on a planet in motion, shaping and being shaped by geological processes. Even though the vents today are home to organisms far more complex than anything that existed billions of years ago, they still offer insights into the possibilities for early life. The chemistry, structure, and energy flows around the vents show that complex systems can emerge in environments that seem harsh but are actually rich in opportunities. The success of vent ecosystems in the present demonstrates how similar ecosystems might have operated in the past. These ideas also extend beyond Earth. Moons like Europa and Enceladus have oceans beneath their icy surfaces. If hydrothermal vents exist there, similar chemical processes could occur. The vents on Earth show that life can thrive without sunlight and in isolation from the surface. If similar conditions exist elsewhere, life could use the same strategies, relying on chemistry rather than light, forming symbiotic relationships and adapting to shifting environments. There is more to uncover about how the vents connect to Earth's early history, including the details of how chemical reactions within chimney structures influenced the development of complex molecules. We'll continue toward these ideas as we look at how these environments remind us that the ingredients for life do not require sunlight or gentle conditions. They require energy, structure, and time, all of which the vents can provide, both in the present and in the distant past. When we think about the vents as reflections of early Earth, it becomes almost impossible not to take the next step and consider what they might suggest about life beyond our planet. The deep ocean is often described as alien, not because it is distant in space, but because it operates under rules that feel different from the ones that guide life at the surface. There is no sunlight. There is no day or night. Vision loses its meaning. Pressure creates an environment unlike anything experienced on land. Heat and chemicals shape the possibilities for survival. The creatures that thrive here do so with structures and processes that seem more suited to science fiction than to the everyday world we inhabit. If such life can be found on our own planet, hidden in the darkness beneath kilometers of water, it raises questions about what might exist in the oceans of other worlds. Earth may not be the only place where hydrothermal vents operate. Several moons in our solar system appear to have global oceans beneath their surfaces. Europa, one of Jupiter's moons, and Enceladus, one of Saturn's moons, are two of the most studied examples. Both are covered in ice so thick that sunlight cannot reach the water below. Yet evidence suggests that beneath the ice lies a liquid ocean, kept warm not by the sun but by tidal forces created by the gravitational pull of their parent planets. These tidal forces generate friction inside the moons, heating them from within. This heat could melt parts of the rocky mantle, creating conditions similar to the ones found along seafloor ridges on Earth. If water seeps into cracks in that rocky mantle, becomes heated, dissolves minerals, and rises back into the ocean, it could create hydrothermal vents in places where sunlight has never touched the surface. Scientists studying these moons have detected signs that support this possibility. On Enceladus, geysers spray water vapour and microscopic particles into space through cracks in the moon's surface. When spacecraft flew through these plumes, they detected tiny grains of silica and traces of hydrogen. Silica grains of a particular size form most readily when water interacts with rock at high temperatures, the same kinds of interactions that occur at hydrothermal vents. Hydrogen is another clue. On Earth, hydrogen is a key fuel for many microbes living near vents. Its presence on Enceladus suggests that chemical reactions might be happening beneath the ice that produce energy in a form life could use. Europa offers its own clues. Its surface is covered with ridges and cracks that appear to shift over time. These changes suggest the ice shell is floating on top of a liquid ocean. Magnetic field measurements indicate that the ocean is salty and electrically conductive, much like Earth's ocean. Models of Europa's interior suggest that heat from tidal flexing could create hydrothermal activity at the seafloor. If vents exist there, they might operate in ways similar to the vents on Earth, releasing mineral-rich fluid, shaping the chemistry of the water, and potentially supporting life that uses chemical energy rather than sunlight. If such worlds exist with oceans, heat, and minerals, the vents on Earth provide a real example of how life might adapt to those settings. The creatures at Earth's vents thrive without sunlight, relying solely on chemical reactions. They tolerate constant darkness. They handle pressures far greater than what humans experience at the surface. They live in an environment that shifts unpredictably as the Earth's crust moves. If life evolved independently on another world, its challenges might be similar, even if the specific circumstances differ. The microbes at vents demonstrate how flexible life can be. They use chemical energy directly from their surroundings. Their metabolic processes are shaped not by sunlight, but by the availability of molecules that release energy when they react. If similar chemicals exist in the oceans of Europa or Enceladus, microbes there could use them in comparable ways. There is no requirement for sunlight in order for biology to function. The vents show that life simply needs a source of energy and a way to capture it. The vents also demonstrate how communities can form around a single energy source. On Earth, tube worms, mussels, shrimp, and other creatures gather around vents because the microbes provide a foundation for the entire ecosystem. If microbes existed on another world, larger forms of life might follow, depending on how evolution shaped them. They may not resemble Earth's animals, but the pattern of life clustering around chemical gradients could appear in any ocean where vents operate. The structure of vent chimneys provides another clue. The minerals that precipitate out of hot vent fluid create surfaces filled with pores and channels. These structures act as tiny shelters, trapping molecules and creating stable environments where reactions occur repeatedly. On early Earth, these structures may have been key to the development of complex molecules. On another world, similar structures could serve as shelters for early chemical processes or even early life. The vents demonstrate how geology can support biology long before complex ecosystems develop. Chemical signatures detected in the plumes of Enceladus offer another intriguing connection to vents. Some of these signatures suggest that the Moon's ocean contains organic molecules. These molecules are not proof of life, but they are the kinds of substances that life could use. If they came from reactions in hydrothermal environments, they might indicate ongoing chemical processes similar to those happening around Earth's vents. The presence of organics, mineral grains, and hydrogen together paints a picture that closely resembles the conditions central to chemosynthesis on Earth. Even the concept of habitability shifts when we look at the vents. On the surface, habitability often refers to areas where sunlight is available, where temperatures are moderate and where water is present. But vents show us that life can form stable communities in environments that lack sunlight entirely, where temperatures swing rapidly, and where chemicals that are toxic to surface life provide the necessary energy. Habitability becomes tied not to light, but to energy and chemistry. If other worlds have these ingredients, they might be habitable even if their surface conditions appear uninviting. Some researchers propose that the earliest life on Earth may have developed around vents. If this is true, it strengthens the idea that vents could foster life elsewhere. The vents create steep chemical gradients, which are essential for driving metabolic processes. They offer sheltered environments with varying temperatures and chemistries. They provide surfaces where molecules can assemble and reorganize. These features could exist in the oceans of other worlds, offering similar opportunities for life to form. Of course, the vents on Earth also remind us of the challenges life might face elsewhere. The chemistry must be right. The water must interact with rock in ways that release energy-rich molecules. The heat must be sufficient to drive reactions, but not so extreme that molecules degrade quickly. The environment must allow for cycles of concentration and dilution. These conditions may exist on some worlds, but not on others. The vents provide a framework for considering what is necessary, not a guarantee. The idea that life might exist elsewhere is not new, but the vents give it a more concrete basis. Rather than imagining life reliant on light, we can imagine life built on chemistry. Instead of imagining Earth-like plants and animals, we can imagine microbes forming dense layers near chemical sources, relying on reactions that parallel those used by vent bacteria. Larger organisms, if they develop, might rely on internal or external symbiotic bacteria in ways that mirror the tube worms, mussels, or shrimp. They might cluster near warm cracks in the seafloor, using temperature cues to navigate their world. They may have bodies shaped to withstand pressure and chemical exposure, much like Earth's vent species. These ideas extend to planets beyond our solar system as well. Some exoplanets discovered around distant stars appear to have oceans. Some are thought to be larger versions of Earth, with thick layers of water covering their surfaces. If these oceans interact with a rocky interior and possess some source of internal heat, hydrothermal systems could exist there too. Life might develop in complete darkness, using chemical energy as its foundation. The vents on Earth show that such ecosystems are possible. In recent years, scientists have used Earth's vents as models for designing missions to explore other ocean worlds. Instruments and probes developed for deep-sea research provide guidance for how to detect chemical signatures that indicate active hydrothermal systems. Concepts for future spacecraft include landers that could melt through the ice of Europa, or orbiting probes capable of sampling the plumes of Enceladus. Each design draws on knowledge gained from studying Earth's vents. If life exists somewhere else, it may leave behind chemical traces similar to those produced by vent microbes. Even the idea of exploring such worlds connects back to the deep sea. Whenever we send submersibles down to Earth's vents, we're practicing a form of exploration that resembles what we might one day do on other worlds. The darkness, the high pressure, and the difficult terrain make deep-sea exploration a challenge. The technologies that allow us to study vents, remotely operated vehicles, autonomous submarines, high-resolution sensors, help scientists imagine how to navigate alien oceans. The vents become both a scientific target and a proving ground for future exploration. The vents also highlight how little we understand about life in extreme environments. Every new discovery around Earth's vents expands our sense of what is possible. For example, microbes capable of surviving at temperatures above 110 degrees Celsius challenge the limits we once thought life could endure. Organisms that rely on chemicals toxic to most known life demonstrate how flexible biochemistry can be. These findings broaden the range of conditions scientists consider when evaluating the habitability of other worlds. Instead of looking for environments similar to Earth's surface, researchers can focus on environments similar to those at Earth's depths. Another clue comes from how vent organisms respond to changes in their environment. They adapt to shifts in chemistry, heat, and pressure. They reorganize their communities when a vent collapses or a new opening appears. This adaptability suggests that life in extreme environments might be more resilient than we assume. If similar processes operate on another world, life there could adjust to changes in geological activity or chemical availability, just as vent species do here. The vents also show how life can remain hidden. Despite supporting dense ecosystems, the vents remained undiscovered until the late 20th century. Their existence was unknown even though they lie on the same planet we live on. If Earth can hide entire ecosystems beneath its oceans, another world could hide life beneath its ice or in its depths. The vents caution us against assuming that we've understood all the possibilities simply because we've explored the surface of a world. When we consider the combination of factors, chemical energy, heat, water, minerals, and structure, the vents become examples of how life can thrive in places that seem, from a distance, inhospitable. They offer a reminder that life looks for opportunities wherever conditions allow. If another world offers similar opportunities, life may take root there, even if it never sees a sunrise. There is still much to learn about how these environments function, how they shape the creatures that live in them, and how similar processes might occur in oceans far removed from ours. We'll continue moving through these ideas as we look at how the deep sea fuels imagination about what could exist in other hidden waters and how the vents guide the search for life beyond Earth, without stepping away from the detailed, grounded view of the creatures and chemistry that allow these ecosystems to thrive. When people first hear about the vents or see the strange organisms clustered around them, it's natural for imagination to fill in the gaps with ideas shaped more by stories than by science. The deep sea has always been a place where the unknown invites speculation. Before anyone had seen tube worms rising like pale pillars around chimneys, before cameras captured shrimp shimmering in heated water, and before researchers understood that entire communities could survive without sunlight, the deep ocean was thought of as a realm where monstrous forms might lurk. Even now, when the science is clearer, the distance and darkness allow myths and misunderstandings to persist. Spending time looking closely at the vents helps untangle these misconceptions and bring attention back to the realities of the organisms that live there. Some misconceptions come from imagining the deep sea as a place dominated by giant, dangerous creatures. Early accounts of ocean exploration included stories about enormous tentacled animals capable of dragging ships under the water, or strange beings with glowing eyes waiting in the depths. These stories weren't based on what we know from vent ecosystems. Most vent organisms are not gigantic or threatening. Tube worms, despite their size, are stationary and gentle. They do not move or hunt. Mussels cluster quietly. Shrimp gather in dense groups but focus their attention on grazing or collecting bacteria. Crabs scavenge rather than chase prey. The creatures here are shaped by the need to survive in a world of chemicals and heat, not by the need to defend themselves from predators like the ones described in myths. This doesn't mean the vent creatures are ordinary. They are unusual, but their unusual qualities come from adaptations rather than fearsome traits. Their extreme shapes and colours have practical purposes. The bright red plumes of tube worms serve to absorb chemicals. The pale exoskeletons of crabs and shrimp reflect the absence of light, not an attempt to look ghostly. The size of the tube worms reflects rapid growth supported by abundant chemical energy, not monstrous proportions born from something unnatural. When their qualities are understood in context, they seem less like the subjects of myths and more like solutions shaped by the environment. There is another misconception that vent creatures are somehow primitive or incomplete, because they live in extreme conditions. Some assume that living without sunlight means organisms are less advanced or less efficient than those in surface environments. In reality, the vent organisms are highly specialized. Their symbiotic systems allow them to use chemicals in ways most animals cannot. Their tolerance for heat, pressure, and toxic substances reflects complex physiological adaptations. Their microbial partners have metabolic pathways that remain active under conditions that would destroy most known life forms. These organisms are not primitive. They are refined products of evolution, shaped by millions of years of selection to thrive in a place where only the most adaptable can survive. Many people also imagine the deep sea as a static environment where very little happens because sunlight does not reach it. This misconception creates the idea that life at the vents must be slow, sparse, or unchanging. The truth is the opposite. The vents are among the most dynamic environments on the planet. Chemical conditions shift constantly. Temperatures fluctuate sharply over small distances. Chimneys grow, collapse, and reform. Species move, reorganize, and respond to new openings and closings. Microbes reproduce rapidly, adjusting to the latest conditions. Some animals grow at surprising rates. Tube worms can add significant length in relatively short periods. Mussel populations can expand quickly when conditions allow. The vents are anything but static. They are centers of continuous change, and the organisms respond to that change with flexibility. A related misconception involves the idea that the deep sea is uniformly hostile, and that all forms of life struggle equally. While the environment is harsh by surface standards, The organisms living there do not experience it as hostile in the same way we might imagine. They are adapted to it. The temperatures and chemicals might seem extreme to us, but for the species living at the vents, these conditions are normal. Their bodies function best under pressures that would crush unprotected equipment. Their metabolisms depend on chemicals that would harm humans. Their sensory systems are tuned to cues we never encounter. To call their environment hostile is to judge it by the wrong standards. For them, it is simply home. Myths also surround how vent animals interact with one another. Because the environment seems harsh, some imagine fierce competition or predation as dominant forces shaping their lives. While predation does occur, it is not the defining feature of the vent ecosystems. Most of the organisms rely on microbes rather than hunting for food. Their energy comes from chemical reactions rather than chasing prey. The need to stay within narrow chemical zones reduces opportunities for dramatic confrontations. The creatures do not roam widely. They cluster near vents where conditions allow them to survive. Instead of imagining dramatic battles or territorial conflicts, it's more accurate to picture communities of organisms adjusting their positions according to gradients in chemicals and temperature. Their interactions are shaped by need rather than aggression. Another misconception relates to the appearance of the vent fluid. The dark plumes rising from the chimneys resemble smoke, which can lead people to imagine fire-like conditions or volcanic eruptions happening continuously. The fluid is not smoke and not the result of burning. It is water mixed with minerals that precipitate as tiny particles when they meet the cold seawater. The black appearance comes from these mineral particles, not from ash or combustion. The process is entirely different from fire. The vents are driven by heat from below, but the water remains liquid despite its high temperature because of the pressure. Understanding this helps shift the image from something fiery to something chemical and geological. There is also a tendency to imagine vent communities as isolated from the rest of the ocean, cut off from any connection to life elsewhere. While they function independently from sunlight, they are not disconnected or irrelevant. The chemicals they release influence ocean chemistry beyond their immediate area. The minerals they deposit form structures that persist long after the vents cool. The organisms that drift away from the vents can contribute to ecosystems farther from the chimneys. Some species move between vent fields over generations, connecting distant communities. The vents are isolated in the sense that they rely on local energy sources, but they are part of the broader ocean environment. Their influence extends beyond their immediate surroundings, and their existence enhances our understanding of how the ocean as a whole functions. In addition to these misconceptions, the unfamiliar appearance of vent organisms sometimes leads to exaggerated impressions. The tube worms, with their long white tubes and red plumes, can look unsettling in images if someone expects more familiar marine life. But their appearance reflects their biology rather than any kind of threat. They are stationary organisms that serve as hosts for symbiotic bacteria. Their bright plumes are simply efficient structures for chemical exchange. Shrimp swarms may look chaotic in footage, with thousands of individuals clustering near vent openings, but their movements reflect precise positioning in temperature gradients rather than frantic behaviour. The pale crabs might seem ghost-like, but their lack of pigmentation is a practical response to a world without light. Some misunderstandings arise from the word extremophile itself. It can imply that these organisms are unusual or unnatural in a way that separates them from the rest of life. In reality, they are part of the continuous spectrum of adaptation on Earth. Every organism survives within a particular set of conditions, whether those conditions involve sunlight, chemical energy, cold water, or warm soil. The vent species simply happen to occupy a part of the spectrum where heat and chemicals play larger roles. They are not outliers in the sense of being unrelated to other life. Their metabolic pathways, genetic material, and cellular structures share similarities with organisms across Earth's biosphere. Their differences arise from adaptation, not from a fundamentally separate origin. Cultural stories about creatures of the deep also shape misconceptions. Tales of sea serpents, leviathans, and other mythical beings often blend with information about deep-sea species. These narratives create a sense that the deep ocean is a place where giant predators lurk unseen. While some deep-sea animals can be large, such as certain fish or squid, the vent communities are not dominated by giants. The organisms here are shaped by limited energy availability and stable chemical conditions. They grow to sizes that reflect the resources they can access. This does not prevent some species from becoming large, compared to shallow water relatives, but none of them resemble the monstrous forms described in myths. There is also a misconception that vent organisms must be fragile, because they live in such specific conditions. While their adaptations are specialised, they are not delicate in the sense that a slight disturbance destroys them. They can withstand shifts in chemistry, movement of the seafloor, changes in vent flow, and pressure that would harm most organisms. Their microbial partners adjust rapidly, providing stability. The larger animals can reposition themselves, move to new locations, or persist until conditions improve. The vent ecosystem is robust, not fragile, despite its specialization. Another misunderstanding is the belief that vent organisms rely on volcanic eruptions for survival. The vents do originate from geological activity, but they do not require eruptions. They rely on steady heat from magma deep below, not explosive events. The presence of vents does not indicate imminent volcanic danger. Instead, the vents reflect slow, ongoing geological processes. The life they support is adapted to heat, minerals and pressure, not to volcanic unpredictability. Some misconceptions come from thinking of the deep sea as empty between vent sites. While vent communities are concentrated around active openings, the areas between vents host their own forms of life, including microbes, small animals, and organisms that drift or swim through the water column. The vents enhance local biodiversity, but they are not the only sites of life in the deep ocean. Understanding this helps prevent the idea that the vents are isolated islands in an otherwise barren world. The idea that the vent species must be lonely or isolated because of the darkness is also a misconception. These organisms do not rely on vision for communication or interaction. Their sensory systems use chemical cues, temperature differences, or water movements. They detect the slightest changes in their environment, guiding them to the right positions. Their interactions are shaped by proximity and chemical gradients rather than by sight. The darkness does not isolate them. It simply shapes how they sense their surroundings. Misconceptions also exist about the danger of vent environments to researchers. While the vents are hazardous in some respects, they are not constantly erupting with boiling water or uncontrollable pressure. The deep-sea vehicles used to study them are designed to withstand pressure, and the movements around vents are carefully controlled. Researchers navigate slowly, avoiding the hottest areas. The vent fields can be studied safely with proper equipment and planning. The vent ecosystems also dispel the idea that life must resemble familiar forms in order to thrive. The organisms here show that life can take shapes we might not anticipate. They reveal that survival strategies can diverge greatly from the ones used by surface species. This does not make them monstrous or strange in a negative sense. It simply shows the diversity of solutions that evolution can produce. There is still more to understand about how myths and misunderstandings arise from partial information or unfamiliar images. As research continues, the reality of these ecosystems becomes clearer, and the creatures living here become defined by their biology rather than by imagined traits. We'll continue moving through these details, keeping close to the real characteristics of these organisms and the environment around them, staying focused on the complexities rather than the stories that once filled the gaps. When we follow the threads of everything happening around the vents, from the geology that feeds them to the organisms that depend on them, a quiet understanding begins to take shape. Life persists here not because the environment is gentle or predictable, but because living systems are capable of finding stability where it seems unavailable. This part of the ocean challenges almost every assumption we might make about what life needs. There is no sunlight. The pressure is immense. The temperatures shift drastically over short distances. The chemicals that pour from the openings are toxic to most known organisms. Yet, instead of emptiness, we find density. Instead of silence, we find activity. Instead of barrenness, we find communities that grow, change and adapt as though the harshness of the environment is simply another set of conditions to work with. The world around the vents doesn't present its difficulty in an obvious way. There are no storms, no waves, no violent movements visible from the perspective of the creatures that live here. The water moves slowly. Darkness remains constant. The chimneys rise steadily from the sea floor. On the surface, stability might mean familiarity, but down here stability takes the form of continuous gradients. The heat flows predictably. The chemistry remains available even if its exact concentration changes. The pressure never relents. The constancy of these features allows organisms to rely on them. That reliability becomes a substitute for sunlight, seasons, and other surface patterns that shape life in shallower environments. When we observe how the organisms behave, it becomes clear that their existence relies on small decisions and steady positioning. Tube worms extend their plumes just far enough to collect the chemicals they need without exposing themselves to lethal temperatures. Their tubes act as anchors, keeping them in place when currents shift. Mussels open and close their shells in slow rhythms dictated by water flow and chemical availability. Shrimp adjust their positions almost continuously, sliding in and out of warmer water to support the bacteria they farm. Crabs explore crevices with deliberate movements, sensing which areas offer the most reliable food sources. These behaviours are not dramatic or sudden. They are measured responses to the environment, shaped by the need to stay within narrow windows of survivability. Despite the dramatic conditions, the atmosphere of the vents feels calm in many ways. There is no sense of urgency in the movements of the creatures. They are not rushing to feed before daylight fades. They are not migrating to avoid seasonal changes. Their challenges are constant, not episodic. This constancy allows them to settle into routines that appear almost peaceful when watched through the lens of a submersible. The water is dark but not empty. The heat rises steadily but not explosively. The chemicals flow, but in patterns that organisms can predict by instinct. Part of the quiet wonder of the vents comes from the way the organisms' relationships shape the landscape. Tube worm clusters form structures that change water flow. Mussel beds help stabilize sediment around the chimneys. Microbial mats alter the chemistry on rock surfaces. These changes accumulate over time, creating microhabitats that support even more life. The organisms do not build intentionally, but their presence creates new conditions that influence the environment in subtle ways. This effect is not unique to the vents. Organisms shape their environments everywhere, but here the interactions stand out because the surroundings are so stark. The microbes form the invisible backbone of the system. They thrive inside rocks, on surfaces, inside animals, and even within the water itself. Their ability to function across a range of chemical and thermal conditions gives the ecosystem its resilience. When conditions shift, the microbes adjust quickly. Their rapid reproduction allows the community to reorganize faster than larger organisms could manage on their own. Their chemical processes stabilize the environment, providing nutrients for the animals and shaping the flow of elements through the system. Without them, the vents would not support anything resembling a community. What makes the quiet wonder of this place even more striking is that the organisms do not seem to resist the environment in a way we might expect. They do not try to escape to more comfortable areas. They thrive because the conditions align with their needs. Heat that would damage other species fuels their metabolisms. Chemicals that would poison other organisms become nutrients. Pressure that would crush most creatures is necessary for their biological processes to function correctly. The harshness of the environment is not an obstacle, it is a requirement. This perspective shifts the way we think about what it means for a place to support life. Instead of looking for environments that resemble the surface world, We can look for environments where energy, structure and chemistry come together in any consistent way. The vents show that life can form tightly linked systems in places where the surface world offers no clue that such systems could exist. This quiet persistence is not dramatic, but it is powerful. It demonstrates how adaptable living systems can be. Some of the wonder comes from understanding how long these ecosystems have existed. Hydrothermal vents today may not be the same vents that existed millions of years ago, but the process that forms them has been active for most of Earth's history. Where vents have appeared, life has likely followed. Over time, lineages have shifted, new species have emerged and older ones have vanished. The constant rebuilding of vent communities shows that life can reassemble itself repeatedly wherever the right conditions exist. The vents almost act as recurring experiments, demonstrating what kinds of organisms and relationships can develop when the basic ingredients are available. Another remarkable aspect is how the creatures here carry the history of their environment within their bodies. The symbioses in tube worms reflect ancient relationships between animals and microbes. The metabolic pathways in the bacteria resemble processes from early Earth. The adaptations in shrimp, mussels and crabs show how bodies can change when energy comes from chemistry rather than light. Studying these organisms reveals not just how life exists today, but how life might have existed when the Earth was young. They become living reminders of how diverse and flexible the early biosphere could have been. The stillness of the vents also hides hints of connection to other parts of the ocean. Even though the communities seem isolated, they are part of larger patterns. Currents deliver oxygen from faraway regions. Minerals released by the vents drift outward, affecting chemistry over broad areas. Larvae travel across long distances before they find suitable vent openings. Microbes detach and drift to other environments. These movements link the vents to the wider ocean, showing how even the most seemingly isolated systems participate in global processes. Part of what makes this environment fascinating is how completely unfamiliar it feels compared to the surface, yet how coherent and functional it is once understood. The absence of sunlight does not create emptiness. Instead, it shifts the starting point of the food web. The constant darkness does not limit the organisms. It removes the need for light-dependent physiology. The pressure does not restrict movement. It provides the structural conditions the organisms require. Sound travels differently here, but the animals do not rely on it. Vision is minimized, but chemical and thermal senses fill the gap. The calm surrounding the vents does not imply stability in the long term. Vents may close, chimneys may collapse, and chemical flow may shift. When this happens, the organisms respond. Some species can linger for a time. Others move when possible. Larvae seek out new openings. Microbes adjust immediately. Communities reorganize around new sources of energy. This cycle repeats endlessly, demonstrating resilience rather than fragility. It is not a loud resilience marked by dramatic survival stories, but a quiet one shaped by gradual adjustments. If we look closely at the chimneys themselves, we see the record of constant change. Layers of minerals accumulate in patterns that reflect the chemistry of the vent fluid. Cracks open and close, deposits build and break apart. These structures grow outward from the Earth's interior as active reminders of the planet's ongoing geological activity. The organisms living around them treat these changes as ordinary. They do not cling to permanence. They accept that their world shifts regularly and continue to adapt without hesitation. The creatures here do not appear desperate or overburdened by their surroundings. Their movements are deliberate, their growth is steady, their reproductive cycles are well timed, their symbioses are stable, their interactions are driven by the gradients of heat and chemicals, not by fear or scarcity. Even in the darkness, the ecosystem maintains a sense of calm progression. Life here is neither chaotic nor stagnant. It is balanced, shaped by the very conditions that seem so unlikely for supporting life. This quiet wonder becomes more noticeable when imagining how the vents would appear to someone encountering them for the first time. The darkness would make it difficult to see at first, but once the chimneys become visible, the scene would feel otherworldly without being threatening. The smooth rise of warm plumes, the clusters of tube worms moving gently with the currents, the shifting patterns of shrimp, the slow steps of crabs, the subtle glow of minerals reflecting the submersible's lights. Nothing seems chaotic or random. Everything fits into a pattern dictated by geology, chemistry, and biology working together. The vents also reveal how life can flourish, even when surrounded by conditions that seem precarious. The environments are confined to narrow ranges around the chimneys. Just outside these areas, the ocean floor becomes colder and less chemically active. Yet within these narrow zones, life thrives. This contrast enhances the sense of wonder. The environment seems strict but generous. It provides only what is necessary, but it does so consistently enough for complex relationships to develop. This consistency relies heavily on the reliability of chemical energy. The microbes can depend on hydrogen sulfide, methane, or other compounds as long as the vent continues to function. The animals depend on the microbes. The community depends on the structure provided by the chimneys. The chimneys depend on the movement of water and heat from below. This chain of dependencies demonstrates how multiple levels of the system support one another. The quiet wonder lies in recognizing how seamlessly these levels interact. Understanding the vents also changes how we think about fragility. Many ecosystems on the surface depend on narrow conditions that can be disrupted easily. The vents depend on narrow conditions as well, but their narrowness is different. The pressure will not change. The darkness will not change. The availability of chemical energy will shift, but it will be replaced elsewhere. The vents show that stability does not always come from mildness. Sometimes it comes from deep, consistent processes that continue regardless of what happens at the surface. Much of the quiet wonder also comes from the idea that these ecosystems exist independently from human influence. They do not depend on our presence or our resources. They continue whether or not they are studied. Their cycles unfold without interference. Their organisms adapt without guidance. The vents remind us that life does not require attention to flourish. It only requires conditions that allow for growth and adaptation. This independence creates a kind of calm that stands in contrast to the more familiar ecosystem shaped by human activity. There is still much to understand about these environments. Researchers continue to study the chemistry of the vent fluid, the genetics of the organisms, the details of their symbioses, and the geological processes that shape the chimneys. Each new discovery adds depth to the picture without disrupting the underlying impression of a system that functions quietly and steadily. The more we study, the more the wonder becomes grounded in understanding rather than surprise. The vents show that life does not need ideal circumstances to persist. It simply needs opportunities. The environments here seem harsh when viewed from the surface, but they provide the energy and structure necessary for survival. The organisms take what is available and build stable systems from it. Instead of struggling against their surroundings, they align themselves with the flows of heat and chemicals. There will always be new questions about how these systems formed, how they maintain themselves, and how they adapt to long-term geological changes. But the quiet wonder lies in realizing that even if we do not have all the answers, the vents continue to function. The creatures continue to grow. The microbes continue to convert chemical energy into life. The chimneys continue to rise from the seafloor. The environment continues to support its residents, demonstrating that life can flourish in ways that challenge our expectations. We remain with this environment for now, following the steady processes that allow life to persist where it seems most unlikely, recognizing that the most surprising thing about the vents is not the heat or the chemicals or the creatures themselves, but the calm and consistent way they come together to create an ecosystem that thrives where most life would fail.